Hello there and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're drifting toward one of the loneliest ideas in astronomy, a planet without a sunrise, a world with no parent star, no familiar orbit, no calendar of seasons, and no warm morning light spilling across its horizon. We're talking about rogue planets, those strange wandering worlds that move through the dark spaces between stars, not because they are villains, of course, despite the dramatic name, but because somewhere in their past they either lost their home or never had one in the usual way. And really, calling them rogue sounds a little unfair, doesn't it? It makes them sound like they have a tiny black cape and a suspicious plan. In truth, they may simply be planets that were pushed scattered, born too small to become stars, or left to wander the galaxy like quiet travellers on a road with no street lamps. Before we move too far into that darkness, let me ask you something gentle. Where are you listening from tonight? Are you somewhere under a cloudy sky where the stars are hidden but still very much there? Are you near a window, in a room lit by a small lamp, maybe with the world outside already settling down? And if you were to step outside and look up, what would you see? A city glow, a few bright planets, the moon, or perhaps just the soft blank ceiling of night? It is a fitting question for this journey because tonight we are not beginning with a bright object that everyone can point to. We are beginning with absence, a missing sun, a missing orbit, a planet that has become almost impossible to see because it has no star shining beside it, no warm spotlight revealing its shape. It is the kind of world that astronomy has to find indirectly, patiently, with methods as delicate as noticing a shadow pass across a candle from another room. And if you find this kind of quiet, cosmic wandering, soothing, intriguing, or simply a good way to let the busy edges of the day soften a little, I would be ever so grateful if you gave the video a like and maybe subscribed. It helps this little corner of calm reach other curious minds who may also enjoy falling asleep somewhere between science and imagination. I do hope tonight's subject does not make the universe feel too lonely, but if it does, perhaps we can make that loneliness a little more understandable, which is often what science does at its best. It does not remove the mystery. It gives the mystery a chair, a warm drink, and a few good explanations. So settle in, let your thoughts slow down, and picture, if you can, a world moving silently through space, not around a star, not toward a sunrise, but onward through the wide, dark lanes of the Milky Way. A rogue planet is, in the simplest sense, a planet that does not orbit a star. That sounds straightforward at first, almost too simple. We're used to thinking of planets as companions: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all travel around the Sun. They may be very different from one another, some rocky, some gaseous, some hot, some icy, some surrounded by rings, some holding moons like little families of their own, but they all belong to the same central arrangement. A star sits near the middle, and the planets move around it, each one following a path shaped by gravity. That is the picture most of us learn early on. A solar system is like a clock, or perhaps a very slow dance, with the star as the bright centre of attention. But rogue planets break that picture. They are not part of a neat family portrait. They are not making yearly loops around a sun. They are out in interstellar space, moving through the galaxy under the broader pull of the Milky Way itself. This is what makes them so strange. A planet to us feels like a place. It feels like ground, weather, gravity, surface, atmosphere, perhaps even oceans or storms. A planet is the sort of thing you can imagine standing on, or flying above, or mapping with patient little spacecraft. But a planet without a star feels like a place with the context removed. There is no dawn to mark direction, no sunset to close the day, no year to count by returning to the same place in orbit. If it spins, it may still have days of a sort, a rotation, a turning of one side away from the deep cold and then back again, but without a nearby sun, that rotation would not create day and night in the familiar sense. It would be more like turning slowly inside a dark room where the lamp has gone out. One side is not really day, the other side is not really night. There is just the faint scattered glow of distant stars, and perhaps, if the planet is young enough or massive enough, some leftover heat leaking from its interior. Now when astronomers speak about rogue planets, they often use more careful names, such as free-floating planets or isolated planetary mass objects. These names may not sound as exciting as rogue planet, but they help avoid giving the world a little too much personality. The word rogue is useful because it is memorable. It makes us imagine a wandering planet crossing the galaxy on its own. But scientifically, the important detail is not rebellion, it is gravity. A rogue planet is not gravitationally bound to a star in the way Earth is bound to the Sun. It may have once belonged to a planetary system and then been thrown out, or it may have formed alone from a small collapsing cloud of gas and dust, in a process that looks more like star formation than ordinary planet formation. That second possibility is especially interesting, because it blurs the boundary between planet and failed star, between a world and a tiny object born in the same nursery where stars begin. There is a bit of a definition problem here, which is exactly the kind of thing astronomy enjoys handing to us just when we thought a word was simple. What makes something a planet? Is it how massive it is? Is it how it formed? Is it whether it orbits a star? In our own solar system, a planet is usually defined partly by its orbit around the Sun, which is why Pluto's classification became such a famous dinner table argument, though hopefully a polite one. But when we leave the solar system and look at planets around other stars, and then planets around no stars at all, the language becomes trickier. If a Jupiter-sized object is floating freely in a young star cluster, is it a planet? If it formed directly from a collapsing cloud, does that make it more like a brown dwarf? A sort of almost star that never grew hot and heavy enough to shine by steady nuclear fusion? Astronomers use mass limits, formation clues, temperatures, spectra, and context to sort these objects, but nature, as usual, did not ask our permission before making the categories messy. One commonly discussed boundary involves deuterium fusion, a kind of nuclear burning that can happen in objects more massive than about 13 times the mass of Jupiter. Above that rough limit, an object may be called a brown dwarf rather than a planet, though even that line is not perfect. Below it, especially when the object is not orbiting a star, we may call it a free-floating planetary mass object. This can feel a little technical, but the basic idea is simple enough. A rogue planet is usually thought of as something with planet-like mass, not massive enough to behave like a star and not attached to a star's gravity. It may be a giant like Jupiter, a colder version of Neptune, or perhaps even a rocky world closer to Earth's size. The smaller ones are much harder to find because they do not glow much on their own, and they do not reflect sunlight from a nearby star. They are, in the most practical observational sense, nearly invisible. Imagine trying to find a black pebble drifting across a dark ocean at midnight, except the ocean is the galaxy. The pebble is thousands of light years away, and your telescope is looking through layers of dust, stars, and cosmic clutter. That is roughly the challenge. Young giant rogue planets can still glow in infrared light because they hold heat from their formation, rather like a baked potato cooling, slowly after being pulled from an oven, though on a much grander and less dinner-friendly scale. These young worlds can sometimes be directly imaged in star-forming regions, where they are still warm enough to be detected. Older or smaller rogue planets, however, may be too cold and faint to see directly. For them, astronomers often rely on gravitational microlensing, one of the universe's more elegant tricks. If a rogue planet passes in front of a distant background star from our point of view, its gravity bends and magnifies the light of that star for a short time. The planet does not shine, but it briefly changes the brightness of something behind it. It reveals itself not by being seen, but by disturbing the light. There is something quietly wonderful about that. A world with no sun, no visible glow, no easy photograph can still leave a fingerprint in starlight. For a few hours or days, a background star brightens in a very particular way, and astronomers read that brightening like a tiny note left by gravity. It is not a permanent signal. The alignment passes, the star returns to normal, and the rogue planet continues on, likely never to be seen again in that exact way. This makes studying them difficult. It also makes them feel strangely fleeting. We are not watching a planet orbit again and again, like we can with many exoplanets that pass in front of their stars on a schedule. We are catching a brief crossing, a single chance meeting between a planet, a distant star, and Earth, all lined up just enough for gravity to do its quiet work. The more astronomers look, the more it seems that these wanderers may not be rare accidents. They may be a major part of the galaxy's planetary population. The numbers are still uncertain, and they depend on how many small worlds exist compared with larger ones, how many are ejected from young systems, and how many form alone. Some estimates suggest there could be billions of giant free-floating planets in the Milky Way. Other models allow for far more, especially if small rocky rogue planets are common. That is a staggering possibility. We tend to imagine the galaxy as a place full of stars, and it is. A starry disk, spiral arms, glowing clusters, bright nebulae, and the soft haze of unresolved suns. But between those stars there may be countless worlds, cold and dim, moving through the dark like stones in a slow, invisible river. The Milky Way might not just be a galaxy of stars with planets attached. It might also be a galaxy of planets that have slipped their leashes or never wore one in the first place. To understand why that matters, we have to gently loosen our ordinary sense of what a planet is supposed to be. We live on a world that is deeply connected to its star. The sun gives us daylight, climate, seasons, photosynthesis, weather patterns, and the energy that drives nearly every familiar part of Earth's surface life. Even our sense of time is tied to the sun. Days are rotations in sunlight, years are orbits around the sun. Morning, evening, summer, winter, all of these depend on being a planet with a star nearby. So when we imagine a rogue planet, we are imagining a planet with most of those familiar anchors removed. It is not just far away, it is not just cold, it is a world whose basic rhythm has changed. A place where the sky might never brighten, where the stars would not rise and set because of a nearby sun but would simply wheel overhead as the planet turns, where warmth, if it exists, must come from within, from radioactive decay, leftover formation heat, tidal forces if it has a companion, or perhaps from a thick atmosphere that traps internal heat beneath layers of pressure. This is why rogue planets are not only strange objects, they are thought experiments made real. They ask us what makes a world a world. Is Earth Earth because it has a surface, because it has gravity, because it has oceans, because it orbits the sun? If Earth were somehow thrown away into interstellar space, it would still be Earth for a while, though not a comfortable one. The oceans would begin to freeze from the top down, the atmosphere would change, the surface would become dark and brutally cold. Yet deep under ice, in the ocean depths, around hydrothermal vents, life might have some chance of continuing for a time, perhaps a very long time, supported not by sunlight but by chemical energy and internal heat. That does not mean rogue planets are likely to be little hidden Earths. Most may be gas giants, ice worlds, or barren frozen bodies. But the possibility reminds us that sunlight is not the only kind of energy in the universe, and a star is not the only source of the planet's story. A world without a sun also changes how we think about home. We often imagine home as a stable place, a planet in orbit, a star in the sky, a system with a centre. But the universe is full of motion, and not all motion is orderly from a human point of view. Young planetary systems can be chaotic. giant planets can shift position. Close encounters can scatter smaller worlds. Stars in clusters can pass near one another and disturb their neighbours. Gravity is not always a gentle organiser. Sometimes it is a bouncer at a crowded cosmic dance, and a planet that formed peacefully in a disk of gas and dust may eventually be tossed out into the wider galaxy. From that moment on, its star becomes just one more distant point of light, fading behind it, no longer a sun but a memory written in motion. So tonight, when we ask, what is a rogue planet really? We're not only asking for a definition, we're asking how a world can become separated from the thing that once gave it light. We're asking how planets form, how systems become unstable, how darkness can hide entire populations of objects, and how much of the galaxy may exist beyond our usual bright-centered view. We're asking whether a planet needs a star to matter. And perhaps, in a quiet way, we're also asking why a lonely object in the dark can feel so compelling to us. Maybe it is because we understand orbits, we understand belonging, we understand what it means to be held by something larger. And so, a world without that holding force naturally catches our attention. Picture one now, not too precisely, because rogue planets may come in many forms. Let it be a large world, perhaps a little like Jupiter but colder, darker and far from any star. Its upper atmosphere is wrapped in clouds that no sunlight touches. Its storms may still move, driven by internal heat and rotation. Lightning might flicker deep inside its atmosphere, briefly illuminating cloud layers that have never known daylight. Above it the sky is black, but not empty. Stars are everywhere, sharper than they appear from Earth because there may be no thick, glowing atmosphere to scatter light, or perhaps softened by a cold haze if the planet has one. There is no sun blazing nearby, no bright disk to dominate the heavens. The galaxy itself may be the largest feature in the sky, a pale band of distant stars arcing overhead, not as scenery but as the broader system this planet now belongs to. Far from any sunrise beyond the warm neighbourhoods of ordinary planetary systems, a lonely planet would drift through space in a way that is both simple and difficult to imagine. Simple, because gravity still guides it. It does not float randomly like dust in a room. It moves through the Milky Way, orbiting the galaxy itself along with stars, gas clouds, clusters, and everything else caught in the galaxy's vast gravitational field. Difficult, because our minds are used to smaller arrangements. We can picture the moon going around Earth, Earth going around the sun, and the sun moving through the galaxy, at least in a general way. But a lone planet, with no nearby star to mark its path, feels like a marble released into an arena so enormous that even the word enormous gives up halfway through the job. A rogue planet is not still. Nothing in the galaxy is still. Even the stars that look fixed in our night sky are moving, each with its own path, speed and history. Our sun travels around the centre of the Milky Way at hundreds of kilometres per second, carrying Earth and the rest of the solar system along like passengers who did not have to buy separate tickets. A rogue planet does something similar, but without the smaller local dance around a star. It follows a galactic orbit shaped by the combined gravity of stars, gas, dark matter, and the galaxy as a whole. If it was ejected from a young planetary system, it may also carry the extra speed of that violent departure. It is not simply wandering in the emotional sense, it has a trajectory, a history written in velocity. If astronomers could know its position and motion precisely enough, they could trace where it is going and perhaps, with enough uncertainty and a very patient computer, where it may have come from. Now, the space between stars is often described as empty, and compared with a planet or a room, or even the air around you, it is wonderfully empty. But it is not truly nothing. Interstellar space contains thin gas, dust grains, magnetic fields, cosmic rays, and stray photons moving between stars. A rogue planet travels through this faint medium like a ship moving through a fog so thin that the ship may go for ages without touching anything large. The distances are so great that collisions between rogue planets and stars, or rogue planets and other planets, are extraordinarily unlikely over ordinary timescales. This is important, because the dramatic imagination may want to send a rogue planet crashing into a solar system, like a cosmic bowling ball. The universe does allow close encounters, and over billions of years some rare captures or disruptions may happen, but most rogue planets probably spend their lives doing something quieter. They drift, they cool, they move between stellar neighborhoods, passing through regions of the galaxy where stars are thick, then regions where they are sparse, usually unseen by anyone and untouched by anything. If you could ride alongside one, which is not a travel recommendation, just a sleepy scientific imagining, the first thing you might notice would be the lack of a dominant light source. On Earth, even at night, we live in a world shaped by the sun. The moon is sunlight reflected back to us. Twilight is sunlight scattered through the atmosphere. The warmth stored in the ground after sunset is sunlight delayed by soil and stone. Even the food in your kitchen is mostly sunlight turned into plants, or plants turned into something else. Remove the sun, and the entire sensory logic of a planet changes. On a rogue planet, the nearest stars may look like stars, not suns. Some could be brighter than others if the planet passes relatively near a stellar region, but most would remain distant points. There would be no great glowing disk crossing the sky, no shadows cast by daylight, no blue noon, no golden evening. The sky might be filled with stars and still provide almost no useful warmth. For a rocky rogue planet, the surface would likely be incredibly cold, unless it had some special source of heat or an unusually thick insulating atmosphere. Without a star, a planet loses surface heat to space. If it is small, like Earth or Mars, that loss can be severe. The atmosphere might freeze out depending on its composition and pressure. Carbon dioxide, nitrogen, oxygen, methane and other gases behave differently under deep cold, but the overall pattern is easy enough to grasp. Take away sunlight and the surface energy budget collapses. The ground radiates heat into space, ice spreads, liquids become solids. Weather as we know it slows or changes completely. There may be winds for a while if the atmosphere remains, driven by internal heat differences or leftover circulation, but it would not be weather under a warming sun. It would be weather in a dark freezer with a planet's interior quietly trying to matter. A giant rogue planet, more like Jupiter, is different. Gas giants already radiate some of their own internal heat. Jupiter, even while orbiting the Sun, gives off more energy than it receives from sunlight, because it is still slowly contracting and cooling from its formation. A young giant rogue planet might glow faintly in infrared, warm from its birth, wrapped in clouds and storms driven from within. It would not be warm in the human sense, at least not at the visible cloud tops, but it would not be a dead frozen stone either. Inside, pressures would climb to astonishing levels. Hydrogen could behave in strange ways. Heat would move outward slowly. Storm systems might roll around the planet for ages. If such a world has moons, and some rogue planets might, then the system becomes even more interesting. A moon orbiting a rogue gas giant could be warmed by tidal flexing, especially if other moons tugged its orbit into a slightly stretched shape. In our own solar system, Jupiter's moon Io is heated by tidal forces until it becomes the most volcanic world we know. Europa may hold an ocean beneath its ice, partly because of tidal heating. A rogue giant with moons could, in theory, carry a little system of hidden energy through interstellar space. That possibility is one reason rogue planets invite such fascinating speculation. They are dark, yes, but dark does not always mean inactive. A rogue planet could have geological heat. It could have radioactive decay inside its rocks. It could have tidal energy if it has moons, or if it exists in a binary arrangement with another planetary mass object. It could have a thick hydrogen atmosphere that traps heat so effectively that, under certain conditions, the surface of a rocky rogue planet might remain warmer than expected. Some scientific studies have explored whether free-floating planets could maintain subsurface oceans beneath thick ice layers, or even surface liquid water under dense atmospheres, though such cases would depend heavily on mass, composition, age, atmosphere, and formation history. We should be careful here. This does not mean the galaxy is filled with cozy hidden Earths wearing winter coats. It means that the word frozen is not always the end of the story. Planets are layered objects. Surfaces can be hostile while interiors remain active. Darkness can sit above heat. For a listener drifting towards sleep, it may be useful to imagine this not as science fiction, but as an extension of things we already know. Earth has life in places sunlight never reaches. Deep under the ocean, around hydrothermal vents, ecosystems survive on chemical energy from the planet's interior. In caves, under ice, within rock, life can be more stubborn and more inventive than the surface alone suggests. This does not prove that rogue planets are inhabited. It does not even prove they are commonly habitable, but it widens the frame. The usual habitability picture places a planet in a star's habitable zone, the region where surface liquid water might exist under the right atmospheric conditions. A rogue planet has no such zone around a star, but it may have internal zones, protected regions beneath ice or within moons, where warmth comes from geology rather than sunlight. The universe, being the universe, is rarely limited to the first diagram we draw. A lonely planet drifting between stars would also experience time differently from the way we normally organise it. Not time in the Einstein sense, though that is always quietly there, but ordinary lived time. On Earth, we count days by sunlight and years by orbit. A rogue planet may rotate, giving it a spin period. It may have a kind of day in the mechanical sense, the time it takes to turn once. But without a sun, that day would not divide light from dark. If the planet has a moon, perhaps the moon would rise and set. If the planet has rings, perhaps they would appear as a faint band against the star field. If the world has auroras from magnetic interactions with the interstellar medium, or from internal plasma processes, then its sky might sometimes glow in curtains or patches, though not in a way we could easily stand under and admire without wearing something more advanced than a winter coat. Seasons would also be strange or absent. Seasons on Earth come from axial tilt combined with orbit around the Sun. A rogue planet might have an axial tilt, but no nearby sunlight to make that tilt matter at the surface. Its calendar would be more like a record of its galactic journey, a sweep around the Milky Way taking hundreds of millions of years. There is a calmness in that idea, and also a kind of scale that makes the mind go quiet. 1 year for Earth is a loop around the Sun. 1 galactic year for the Sun is a loop around the Milky Way, taking roughly hundreds of millions of Earth years. A rogue planet belongs to that larger rhythm directly. It does not have a local year around a star. Its great circuit is around the galaxy, through spiral arms, past star-forming regions, across gravitational tides and long stretches of dimness. During one galactic orbit, stars are born, massive stars explode, clusters loosen, and civilizations, if they arise, may come and go many times over. The planet continues. If it is a cold, rocky world, its surface may barely change. If it is a giant, it slowly cools. If it has moons, they circle it in the dark, making a tiny system without a sun. It is not empty of motion. It is full of slow motion. How does a planet become this kind of traveller? The most familiar route begins in a young planetary system. Planets form in disks of gas and dust around newborn stars. At first, the system can be crowded and unsettled. Young planets tug on one another. Gas in the disk can make them migrate inward or outward. Large planets can disturb smaller bodies. Close encounters can exchange energy, and in orbital mechanics, energy is destiny. If one planet gives another too much orbital energy during a close gravitational interaction, the unlucky one may be flung onto a path that no longer loops back around the star. It crosses the escape threshold and leaves. The The event might not look explosive from far away. There is no flash, no dramatic snapping sound, no little sign saying, "You are now exiting the solar system." It is simply a change in orbit. A planet that once belonged no longer does. A second route involves stellar encounters, stars often forming clusters, not alone. In a crowded young cluster, another star may pass close enough to disturb a planetary system. Its gravity can stretch or scramble orbits, especially for planets far from their host star, where the star's grip is weaker. A planet in the outer regions of a system may be stripped away or nudged into instability. It may be captured by another star, thrown into a wider orbit, or released into interstellar space. This is not the everyday fate of every planet, but over the history of a galaxy, with many stars and many systems, the numbers can add up. Gravity does not need to be violent often to produce a large population over billions of years. It only needs patience, and the universe has a great deal of that. There may also be planets, or planet mass objects, born alone. In star-forming regions, clouds of gas and dust collapse under gravity. Usually a collapsing clump becomes a star or a brown dwarf if it gathers enough mass. But if a clump is too small, it might form an object with only a few times Jupiter's mass. It would look like a planet in mass, but its origin would be more star-like. These objects complicate the story, because they are free-floating from birth rather than exiled. They were not thrown out of a system. They never had a star in the first place. A lonely beginning, perhaps, but not a tragic one. The universe does not assign sadness to formation mechanisms. That is something we bring with us, tucked into our human way of understanding separation and home. Finding these different histories is one of the major scientific challenges. If astronomers detect a free-floating object, how do they know whether it formed around a star and was ejected, or formed by itself from a small cloud? Mass helps, age helps, composition helps, location helps. A young cluster full of newborn objects may reveal warm planet mass bodies that formed recently, perhaps like stars. A brief microlensing event in the galactic bulge may reveal an older, colder planet, passing in front of a distant star, but it may tell us very little about that planet's origin. Future surveys, especially those designed to catch many microlensing events, should help build a statistical picture. One or two wanderers are mysteries. Hundreds or thousands become a population, and populations can tell stories that individual objects keep hidden. Think of it like hearing footsteps outside in fresh snow. One set of tracks tells you something passed by. Many tracks over many nights tell you the habits of the whole forest. Rogue planets are like that. A single detection is thrilling, but a census is transformative. How many are there? Are most giant or small? Are they more common in certain parts of the galaxy? Do young clusters produce them in large numbers? Do planetary systems eject them frequently? Are Earth-mass rogue planets common or rare? These questions matter because they reflect how planetary systems form and survive. A solar system is not just a neat final arrangement. It is the result of construction, collisions, migration, clearing, scattering, and long-term stability. Rogue planets are the pieces that may have been left out, thrown out, or made in another way entirely. They are not exceptions to planet formation. They may be one of its normal outcomes. From the planet's own point of view, if we can gently pretend it has one, the galaxy would be both home and wilderness. It would not pass stars the way a person passes houses on a street. The spaces are too wide. Even in denser regions, stars are separated by enormous distances. A rogue planet might spend millions of years with no close stellar encounter at all. When it does pass nearer to a star, that star may brighten in the sky for a time, perhaps becoming more than just another point, but still very far away compared with the Sun from Earth. If the encounter is close enough, the star's gravity might bend the planet's path. In rare cases, a rogue planet could even be captured into a new system, though capture usually requires a way to lose energy, often through interaction with another body. More commonly, It would pass by and continue, changed slightly, like a traveller whose route curves around a distant city without ever entering it. The darkness around such a world is not empty darkness. It contains the light of the galaxy. From Earth, our night sky is softened by atmosphere, moonlight, human lighting, and the fact that our eyes are not built for long astronomical exposures. From a rogue planet with a thin or absent atmosphere, the stars might look incredibly sharp. The Milky Way could be a bright structured band, especially if the planet is in a region with a clear view of the galactic plane. Nebulae might appear as faint smudges. Nearby young stars might glow blue-white. Red dwarfs might be small ember-like points. If the planet is in a dense star-forming region, the sky could be richer. If it is in a more isolated part of the galaxy, the sky could be sparse. But even the brightest starry sky would provide only a fraction of the energy a close sun gives to a planet. It would be beautiful, perhaps, but beauty is not the same as warmth. A rogue planet also asks us to rethink the emotional language we attach to space. We call it lonely because it lacks a star. We call it wandering because it has no orbit around a sun. We call it rogue because it is unattached. But physically it is still part of the galaxy. It still belongs to gravity. It is still surrounded by the long history of cosmic matter. The atoms in its rocks or gases were made in stars, supernovae, stellar winds, and ancient clouds. If it formed in a disk around a star, then it carries the chemistry of that birthplace. If it formed alone, it still condensed from interstellar material enriched by earlier generations of stars. It is not separate from the universe. Nothing is. It is simply separate from the kind of local arrangement that we find familiar. That may be the quiet lesson hidden in these starless worlds. A planet can lose its sun and still remain a planet. A world can leave a system and still follow laws, carry heat, hold moons, bend light, and move through a larger home. It can be almost invisible and still numerous. It can be cold and still geologically interesting. It can be lonely in our imagination, and yet connected by gravity to the entire Milky Way. A planet does not usually leave home all at once. It begins, most of the time, as part of a very ordinary cosmic family, if ordinary is a word we are allowed to use for a spinning disk of gas and dust around a newborn star. There is a young sun in the middle, still hot and restless, still wrapped in the leftover material from its own formation. Around it lies a wide, flat, messy disk, filled with dust grains, ice, rock, gas, clumps, turbulence, and all the tiny beginnings of worlds. Nothing about it looks calm yet. It is not the neat picture we see in a school diagram, with tidy planets placed at comfortable distances and polite labels underneath. In the beginning, a planetary system is more like a crowded kitchen during a family holiday, with everyone moving at once, someone opening the oven, someone looking for a spoon, and at least one object probably about to fall off the counter. Gravity is in charge, but gravity is not always gentle. It can build a home, and it can also decide that one member of that home is going to be shown the door. To understand how a planet gets thrown into the dark, we have to begin with the idea that orbits are not simply paths. They are balances. A planet stays around a star because it is moving sideways fast enough not to fall straight in, but not fast enough to escape completely. It is always falling, in a sense, but always missing the star. That is what an orbit is, a kind of endless, graceful missing. Earth falls around the Sun this way, Jupiter does it, Neptune does it. Even comets with their long, stretched paths are held by the Sun unless something gives them too much extra energy. And that little phrase, extra energy, is where the trouble begins. If a planet gains enough orbital energy, it can cross the boundary between being bound and being unbound. It no longer makes a closed loop around its star. Its path opens outward. The star's grip weakens with distance. And eventually the planet is no longer a planet of that star at all. It has become a traveller of the galaxy. This sounds dramatic, almost like a cosmic explosion, but most of the time, there is no bright flash when it happens. There is no sudden crack in space, no alarm bell, no signpost that says, "Now leaving your solar system. Please check you have all moons and personal belongings." A planet can be ejected through pure orbital mechanics, through a series of close gravitational encounters with other planets. One world passes too near another. Their gravity pulls on each other. They exchange energy and momentum. One may be pushed inward, perhaps onto a tighter orbit. Another may be flung outward. The star remains at the centre, doing what it has always done, but the planets are not merely passive marbles rolling around it. They tug, they shove, they disturb one another. And in a young system with several massive planets, those disturbances can build into a long, slow instability. Imagine 2 planets forming too close together, or 3 giant planets settling into orbits that are almost, but not quite, stable. At first, everything may seem fine. They circle the star again and again. But each time they pass certain points, their gravitational tugs add up. A tiny change here, a tiny change there, a slight stretch to one orbit, a small shift in timing. Over thousands or millions of years, these small effects can become large ones. The planets may enter orbital resonances, where their periods line up in repeating patterns, so one tug comes at just the right moment to strengthen the next tug. Resonances can be beautiful and stable, like the orbital dance of some moons, but they can also become a kind of gravitational argument that nobody wins. Eventually, one planet's orbit may become more oval, another's may shift, their paths may cross, and once planetary paths cross, close encounters become possible. A close encounter between planets is not like 2 cars passing on a narrow road. Space is wide, and the planets themselves may never come physically close enough to collide. But gravity reaches across distance. A massive planet, especially a gas giant, can act like a gravitational slingshot. If a smaller planet passes near it, the smaller planet can steal a bit of orbital energy from the giant, or lose some, depending on the geometry of the encounter. The giant planet barely notices, at least compared with the smaller one, because it is so massive. But the smaller world may have its orbit completely transformed. It might be thrown inward toward the star, perhaps doomed to become a scorched close-in planet or fall into the star entirely. It might be tossed into a long stretched orbit like a comet, or it might gain enough energy to leave forever. There is something almost unfair about this, but gravity is not concerned with fairness. A giant planet can dominate the architecture of a system. Jupiter, in our own solar system, has shaped the asteroid belt, influenced comets, tugged on other planets, and generally behaved like the large relative at a quiet dinner who does not mean to take up the whole room but somehow does. In young planetary systems, multiple giant planets may form, and if they end up too close to one another, they can scatter each other like heavy dancers losing the rhythm. One giant may be thrown outward while another moves inward. Sometimes the ejected object is small, sometimes it is a Neptune-like world, sometimes it might be a gas giant itself. The final system left behind can look calm, but that calm may be the aftermath of a storm. A few stable planets remain, moving in neat orbits, while one or more others have been sent away into interstellar space. Our own solar system may have had a more restless youth than its current arrangement suggests. The giant planets likely did not form exactly where they are today. They migrated, shifted, and interacted with leftover planetesimals, those smaller building blocks of planets. Models of the early solar system suggest that the outer planets may have moved significantly while scattering smaller icy bodies through the young system. Some versions even propose that an extra giant planet may once have existed and later been ejected. We do not know that with certainty, and we should not pretend that every model is a diary entry from the solar system itself. But the idea is useful. Planetary systems can rearrange themselves. What we see now is not always what formed first. A calm system may be a survivor's photograph taken long after the messy family argument ended. For a planet that gets ejected, the process may take a long time. It might not be one dramatic shove. It may be a series of encounters, each one stretching the orbit a little more. First, the planet's path becomes slightly eccentric, meaning less circular and more oval. Then perhaps it crosses the orbit of another planet. Then it has a close pass. Then another. Each encounter changes the numbers. The planet's closest approach to the star, its farthest distance, its speed, its tilt, all of these may shift. It might spend thousands or millions of years on a strange elongated orbit, returning again and again to the inner system like a nervous visitor who has not quite left. Then, after one final encounter, its path opens. It will never come back. The star that once filled its sky begins to shrink behind it. At first, the star would still matter. If the ejected planet were rocky and had an atmosphere, it would still receive some warmth for a while as it moved outward, though less and less with distance. Sunlight fades quickly because it spreads out in all directions. Double the distance from the star, and the light drops to 1/4. Move 10 times farther out, and it is 100 times weaker. Farther still, and the star becomes a bright point rather than a sun. The planet's surface cools, its weather changes. If it has oceans, the top layers begin to freeze. If it has clouds, they may collapse into snow or frost depending on their composition. If it has a thick atmosphere, that atmosphere may slow the cooling, but it cannot replace the steady warmth of a star forever, unless the planet has other strong internal sources. If it is a gas giant, the change is different. It may never have had a solid surface in the ordinary sense, and its deep heat may keep it glowing faintly in infrared for a long time. But the visible sunlight on its cloud tops fades all the same. A planet thrown outward from a young system may carry moons with it, though not always. This is one of those details that makes the story feel wonderfully complicated. A moon is bound to its planet, but if the ejection process involves close encounters with other massive planets, those encounters can strip moons away. A moon orbiting far from its planet is more vulnerable. A tight moon may survive. If the rogue planet escapes with a moon, then the darkness is not entirely solitary. The planet has a companion, a smaller body still circling it, held by local gravity, even though both are no longer held by the star. This little two-body system might continue for billions of years. If there are multiple moons, their gravitational interactions could create tidal heating. A moon might flex as it orbits, its interior warmed by the constant tugging. In the dark between stars, such tidal warmth could matter far more than starlight. It would not create a sunny day, but it might keep geology alive, perhaps even keep a hidden ocean from freezing completely. Another way planets can be thrown into darkness involves the wider environment where stars are born. Stars often form in clusters, and clusters can be crowded places, at least by astronomical standards. Our Sun today has plenty of space around it, with the nearest star system more than 4 light-years away. But in a young cluster, stars can pass closer to one another. Their gravity can disturb the outer regions of planetary systems, especially planets that formed far from their stars. A planet close to its star is held tightly. A planet far away is held more loosely, like a person standing at the edge of a crowd, easier to pull away. If another star passes close enough, it can tug that outer planet onto a new path. The planet might be stolen, captured into the passing star's system. It might be pushed inward or outward, or it might be released entirely, no longer belonging to either star. This kind of stellar flyby can sound rare, and in mature, quiet neighbourhoods like ours it is. But the early life of a star can be more social. A newborn system may spend its first millions of years near many siblings, stars born from the same giant molecular cloud. During that time, gravitational encounters are more likely. The outer planets, dwarf planets, comets, and icy bodies are especially vulnerable. In a system with a wide-orbit giant planet, a passing star might provide the final nudge that turns an already delicate orbit into an escape route. It is another reminder that a planet's fate is not decided only by the star it orbits. The surrounding stellar neighbourhood can matter too. A solar system is not born in isolation. It forms in a galaxy, inside a cloud, among other stars, with gravity reaching in from every direction. Binary stars add another layer of difficulty. Many stars are not alone. They have stellar companions, and planets can form around one star in a binary or around both stars together. These systems can be stable, but they also have more moving parts. If the binary orbit is wide, planets around one star may survive comfortably. If the companion star comes close or follows an eccentric path, its gravity can disturb planetary orbits over time. The planet may not feel a sudden yank. Instead, its orbit can slowly tilt, stretch, and shift through repeated gravitational influence. Some planets may be driven into the star, others may collide, others may be thrown away. In such systems, the path to becoming a rogue planet may be less like being kicked out in one moment, and more like living in a house where the floor very gradually becomes steeper until one day you slide out the door. There are even more extreme situations. If a star loses mass late in its life, perhaps as it becomes a red giant and sheds its outer layers, the gravitational grip on distant planets weakens. A planet that was once bound at a great distance may find itself less securely held. If other planets are present, their interactions can become unstable after the star changes. Around white dwarfs, neutron stars, or stellar remnants, planetary systems can be rearranged in dramatic ways. A supernova, in the case of a massive star, can remove mass violently and kick the remnant, disrupting any planets that survive the event. This is probably not the main way most rogue planets form, especially because many planets would not survive close involvement with such violent stellar evolution, but it shows that the universe has several ways to loosen a star's hold. Gravity builds systems, but changing mass, passing stars, and planet-planet encounters can all rewrite the architecture. The quiet phrase, escape velocity, helps tie these ideas together. To leave a star, a planet must move fast enough that the star's gravity cannot pull it back into a closed orbit. Near the star, the required speed is high. Far away it is lower. This is why planets in the outer system are often easier to eject than planets close in, at least in simple terms. They are already near the edge of the star's deep gravitational well. A modest push from a giant planet or passing star can be enough. For inner rocky planets, ejection may require stronger interactions, but it is still possible, especially in crowded systems. A young system with giant planets migrating through it can scatter rocky worlds before they settle into stable orbits. Some may be lost inward, some may collide, some may be thrown outward. The final arrangement of planets can be only a fraction of the original experiment. And what happens to the planet during the ejection itself? Not much in the immediate physical sense, unless it suffers close tidal stresses, collisions, or atmospheric stripping. The planet does not feel a single clean moment when it becomes rogue. There is no surface announcement. A mountain on the world, if it has mountains, does not know that the orbit has opened. An ocean does not instantly freeze at the boundary of escape. The changes come gradually as distance increases and starlight fades. If any life existed there, which is a very big if, its fate would depend on where that life lived and what energy source it used. Surface life relying on sunlight would be in grave trouble. Photosynthesis would fail as light weakened. Temperatures would drop. Ecosystems would collapse or retreat. But deep subsurface environments, if they existed, might be less immediately affected. A biosphere supported by chemical reactions near hydrothermal vents would care much less about whether there was sunlight overhead. It would still depend on heat, chemistry, water, and stability. A rogue Earth would be a catastrophe for surface life, but perhaps not an instant end to every possible hidden microbe. The dark is not gentle, but it is not always absolute. There is a strange emotional weight to all this, because when we talk about a planet being ejected, We naturally imagine exile. We imagine a home lost. But from the point of view of physics, it is simply an exchange. The planet gains energy. The system changes shape. Momentum is conserved. One object's path opens, another's tightens, and the star continues shining. The language of loss belongs to us. It comes from living on a world where the sun is so central that removing it feels almost unthinkable. We are sun-like creatures, even at night. Our food, climate, calendars, religions, myths and moods are tangled with the star above us. So a planet without a star feels like a sentence without its main verb. Still present, but missing the action we expected. Yet the planet itself may remain whole. That is important. Being thrown into the dark does not necessarily mean being destroyed. A rogue planet may be a survivor. It may carry scars from its formation, a tilted axis from an ancient impact, moons that endured the escape, an atmosphere slowly freezing or thickening, a hot interior cooling grain by grain across vast time. If it is a young giant, it may still glow invisibly to human eyes, radiating heat in wavelengths our bodies cannot see. If it is rocky, it may become a frozen shell around a warmer heart. If it has a thick hydrogen atmosphere, the pressure and insulation might create unexpected conditions far below the cloud tops. The surface, if there is one, may never see dawn again, but the interior still remembers that planets are not just surfaces. They are deep machines of pressure, heat, chemistry, and time. This is why ejection is not only a story of separation, it is also a story of what remains. The planet loses its star, but it keeps its mass. It keeps its gravity. It may keep its moons. It keeps the angular momentum of its spin. It keeps radioactive elements in its rocks, if it has them. It keeps heat from formation slowly leaking away. It keeps its path through the galaxy. And perhaps most importantly for astronomers, it keeps the clues of its past. Its mass, composition, temperature, atmosphere and motion may all carry hints of where it came from. A free-floating object in a young star-forming region may tell one story. A micro-lensing event caused by a cold planet in the galactic bulge may tell another. A rogue planet with a surviving moon would tell another still, because moons can reveal how gentle or violent the ejection may have been. The actual moment of escape, if we could watch it from far away over a sped-up timescale, might look almost graceful. The planet moves in its stretched orbit, returns once more toward the inner system, passes near a giant planet, and then departs on a path that does not bend back. The star grows smaller behind it. The other planets continue their loops, perhaps slightly altered by the same encounter. The system has lost a world but gained stability. This is often how nature works. Disorder in the beginning can lead to order later. A planetary system may eject several bodies before it settles into a long-lasting arrangement. The rogue planet is not an error. It may be the price paid for stability elsewhere. Somewhere, a remaining planet enjoys a calmer orbit because another world took the excess energy and left. That thought makes rogue planets feel less like cosmic accidents and more like hidden evidence. Every wandering world may be a clue to a system we cannot see, a system that once formed more planets than it could keep. The galaxy's dark spaces may be filled with the leftovers of ancient gravitational negotiations. Some were thrown out by giant planets, some were loosened by passing stars, some were unsettled by binary companions. Some may have formed alone and never belonged to a star at all, which is a different mystery waiting just beyond this one. But for the ejected worlds, the basic story is clear enough to hold in mind as you rest. A planet forms in a crowded young system. Gravity shifts and tugs. Orbits stretch. A close encounter gives one world too much speed. The star's grip fails, and the planet begins its long movement into the spaces between stars. From then on, it lives under a different kind of sky. Its old sun becomes one more point of light, lost among billions. Its path is no longer measured in local years, but in the wider sweep of the Milky Way. It may pass through spiral arms, through dim regions, through the outskirts of clusters, through thin gas and dust. It may never again feel strong starlight. It may never again have seasons in the way Earth does. But it is still moving, still cooling, still held by the larger gravity of the galaxy. That possibility is where the story becomes even stranger, because not every lonely planet may have been thrown away. Some may not be exiles at all. Some may have begun in darkness from the very start, not as planets circling a young star, not as members of a solar system that later became unstable, but as small isolated objects forming on their own from the cold material between stars. And if that sounds as if nature is quietly bending the rules when no one is watching, that is because nature does this quite often. We draw tidy lines. The universe smudges them. We say, here is a star, here is a planet, here is a failed star, here is a cloud, here is a world. Then the cosmos places something between those categories, folds its arms, and waits for the astronomers to argue politely over coffee. The question is simple to ask and very hard to answer. Can a planet be born without a star? Not just lose one later, not get kicked out by a larger neighbour, not escape after a close encounter, but actually form alone, directly from a small collapsing piece of a cold interstellar cloud. At first, this sounds wrong because we usually learn that planets form in disks around stars. A star is born from a collapsing cloud. Leftover gas and dust swirl around it. Dust grains stick together, pebbles become rocks, rocks become planetesimals, planetesimals collide and gather. Eventually planets emerge from the disk like loaves rising in a very dusty cosmic bakery. This is the standard picture, and it works beautifully for many worlds. Earth, Jupiter, Saturn, and countless exoplanets likely grew in this way, inside the flattened nursery of material around a star. But free-floating planetary mass objects ask whether there is another route, a quieter, smaller version of star formation that stops before it ever becomes a true star. To picture this, imagine a giant molecular cloud, one of those enormous dark regions of gas and dust where stars are born. These clouds are cold, vast, and uneven. They are not smooth blankets. They are more like weather systems made of hydrogen, carbon monoxide, dust grains, magnetic fields, turbulence, and gravity. In some places, the cloud becomes denser. A pocket of gas begins to collapse under its own weight. If enough material gathers, the center heats up, pressure rises, and eventually a star ignites. That is the grand version. But what if the collapsing pocket is small? What if it gathers enough mass to become a round object, enough to glow faintly with leftover heat, enough to have an atmosphere and a deep interior, but not enough to ignite hydrogen fusion like a star? Then you may get a brown dwarf, often called a failed star, though that sounds a little harsh, as if the object simply did not study hard enough for its stellar exams. A brown dwarf is more massive than a planet, but less massive than a true star. It can form like a star from cloud collapse, but it never becomes hot and massive enough in its core to sustain the long-term hydrogen fusion that makes stars shine for millions or billions of years. Some brown dwarfs can briefly fuse deuterium, a heavier form of hydrogen, if they are massive enough, but they do not become steady suns. They cool over time, fading in infrared, like embers that never became a campfire. This is where the boundary becomes awkward. If a lonely object is 13 times the mass of Jupiter, or 10 times, or 5 times, and it formed alone from a collapsing cloud, what should we call it? A planet? A sub-brown dwarf? A planetary mass object? A world-sized almost star? Science prefers careful labels, but even careful labels can wobble when nature builds something in the middle. The deuterium-burning boundary is often used as a rough dividing line. Around 13 Jupiter masses, depending on composition and other details, an object may become massive enough to fuse some deuterium early in its life. Above that line, astronomers often call the object a brown dwarf. Below it, if the object has a planet-like mass, the language becomes more flexible. If it orbits a star, we are more comfortable calling it a planet. If it floats alone, the name depends on what the scientist is trying to emphasize. Some call these objects free-floating planets. Some call them isolated planetary mass objects. Some prefer sub-brown dwarfs, especially if they formed like stars. This may sound like a naming problem, but it is more than that. The name carries a story. A planet suggests birth in a disk. A sub-brown dwarf suggests birth by cloud collapse. A free-floating planetary mass object is the cautious option, the scientific equivalent of saying, "We know what it looks like, but we are not ready to commit to its childhood biography." This matters because formation is one of the deepest questions in astronomy. Two objects can have similar masses and temperatures, yet completely different origins. Imagine two lonely Jupiter-sized worlds drifting through a young star-forming region. One may have formed around a star and been ejected by a gravitational encounter. The other may have formed alone, directly from a small fragment of gas. They may look similar through a telescope. Both may be faint, red, warm in infrared, and unattached to any star. But their pasts are not the same. One is a former planet in the traditional sense, born in a disk and later thrown away. The other is more like a tiny failed star, born alone and never given a central sun. From a distance, they wear the same dark coat. Underneath, their stories are different. How could astronomers tell the difference? Carefully and not always with certainty. Location helps. If many free-floating planetary mass objects are found in a young star-forming region, that suggests at least some may have formed there recently, perhaps alongside stars and brown dwarfs. Age helps too. Young objects are warmer and brighter in infrared because they still carry heat from formation. Their motions can reveal whether they belong to a nearby stellar association, a loose family of young stars born in the same region. Their spectra can show chemical fingerprints, surface gravity, temperature, and atmospheric features. A very young, low-mass object may have a puffier atmosphere and lower surface gravity than an older field object of similar temperature. These are clues, not perfect answers. Astronomy is often like solving a mystery from footprints left in fog. One fascinating clue comes from accretion. Young stars often grow by pulling in gas and dust from surrounding disks. The material spirals inward, heats up, and produces distinctive signals. Brown dwarfs can also have disks and accrete material, and now astronomers have observed young free-floating planetary mass objects showing behaviour that looks surprisingly similar. Some appear to be surrounded by disks of gas and dust. Some show signs of actively feeding from their surroundings. That is a remarkable thought. A lonely planet-like object, not orbiting a star, can still have a little disk of its own, a tiny version of the structure we associate with starbirth. It may not have a sun, but it can still have a nursery. It may not be a planet in the tidy solar system sense, but it can still grow from material falling in around it. This is where the question becomes almost philosophical, though we will keep it comfortable and not let it steal the blanket. If an object has the mass of a giant planet but forms the way a star forms, is it really a planet? If it never orbited a star, never grew in a protoplanetary disk, and never belonged to a planetary system, then the word planet begins to feel less certain. But if it is only a few times Jupiter's mass, if it is round, cold, atmospheric, and unable to shine like a star, it also does not feel quite like a brown dwarf in the ordinary sense. We are left with a middle category, one of those scientific borderlands where the interesting things often live. The universe has many borderlands, between planet and star, between moon and planet, between comet and asteroid, between gas cloud and galaxy. We should not be surprised that rogue worlds occupy one of these in-between places. The formation of a star-like planetary mass object requires a small cloud fragment to collapse. This is not easy, because gas pressure, turbulence, magnetic fields, and heat all resist collapse. Gravity has to win locally. For a full star, gravity gathers a large amount of mass. For a brown dwarf or planetary mass object, the collapse must somehow stop small. Several mechanisms might help. Turbulence in a molecular cloud can create dense clumps of many sizes. Some clumps may be small enough to form low-mass objects directly. Radiation from nearby massive stars can erode larger clumps, stripping away material before they grow into full stars. Interactions in young multiple star systems can eject forming embryos before they have time to accrete much mass. In that last case, the object begins star-like but is thrown out early, becoming low mass because it was cut off from its food supply. So even the phrase "born without a star" can hide several different pathways. The universe does enjoy making sure the simple answer is not the whole answer. One possibility is direct fragmentation. A cold cloud breaks into pieces, and one of those pieces is simply small. It collapses into a planetary mass object without ever needing a central star nearby. This would be the cleanest version of a born-alone rogue planet, though even here the word planet is debated. Another possibility is embryo ejection. A small protostar begins to form in a crowded nursery with other forming stars. Before it gathers enough mass to become a star, gravitational interactions fling it away from the dense gas that was feeding it. It survives as a low-mass brown dwarf or planetary mass object. This is like being removed from the buffet after one bite, which is rude, but cosmically effective. A third possibility involves photoevaporation near massive stars. A forming object begins inside a larger gas clump, but intense radiation from nearby hot stars strips away the outer layers, leaving behind a low-mass core. In each case, the result could be an object with planet-like mass, but a star-like origin. What makes this especially challenging is that ejected planets and star-like planetary mass objects may overlap in mass. A young giant planet thrown out of a system might be 5 times Jupiter's mass. A small cloud collapse object might also be 5 times Jupiter's mass. A telescope sees faint infrared light. It sees an atmosphere. It measures temperature. It estimates mass using models, age, and brightness. But it may not immediately see the object's birth certificate. This is why astronomers look at populations. If a young association contains far more free-floating planetary mass objects than expected from simple star-like formation, perhaps many were ejected planets. If their numbers follow the same mass distribution as brown dwarfs and stars, perhaps more formed by cloud collapse. If they have disks, accretion, and motions matching young stellar populations that support star-like formation for at least some. If microlensing reveals a huge population of cold Earth mass objects in the older galaxy, ejection may become a more likely explanation for many of them. Different methods see different pieces of the puzzle. Young regions like Upper Scorpius and Ophiuchus have been especially important because they are relatively nearby by galactic standards and full of young objects. Young free-floating planets are easier to detect than old ones because they are still warm from formation. They glow in infrared, not brightly like stars, but enough that careful surveys can pick them out from the background. In such regions, astronomers have found large samples of candidate free-floating planets, objects with masses comparable to giant planets. These discoveries do not settle every origin question, but they show that the galaxy can produce many unattached planetary mass objects in star-forming environments. It is one thing to imagine a lone wanderer as a rare cosmic oddball. It is another to find a whole population, scattered through a young association like dark seeds that never planted themselves around suns. A disk around a free-floating planetary mass object deepens the mystery in a lovely way. We tend to think of disks as belonging to stars because planets form from them. But if a very low mass object forms like a star, it may have a scaled-down disk too. That disk could, in theory, form moons or small companion bodies, so a lonely planet-like object might have its own miniature system, a faint central body surrounded by leftover material, perhaps with tiny moons forming from a disk around it. It would be like a solar system reduced to a whisper. No star, no blazing centre, just a warm, young planetary mass object and a delicate ring of gas and dust settling around it. If that does not sound like the universe quietly inventing a new category, while our textbooks are turned the other way, I am not sure what does. The difference between a rogue planet and a brown dwarf is not only about mass or formation, it is also about heat and light. A true star holds itself up partly through the energy released by sustained hydrogen fusion. It shines for a long time because its core is a furnace. A brown dwarf may briefly burn deuterium, or, if massive enough, lithium, but it eventually cools and fades. A planetary mass object below the deuterium burning limit cannot even do that in the same way. It is born hot because collapse and formation release energy, then it cools over time. Its brightness is mostly a memory of its birth, slowly leaking away. This means a young object can be visible in infrared, while an older one of the same mass can become almost impossible to see directly. Two lonely worlds of similar mass may differ dramatically depending on age. One is still warm enough for our telescopes to find, the other has cooled into darkness, detectable only by gravity if it passes in front of a background star. This cooling also affects how we imagine the object physically. A newly formed free-floating planetary mass object may be swollen, hot, cloudy, and dynamic. Its atmosphere could contain molecules like water vapor, methane, carbon monoxide, or dust grains depending on temperature. As it cools, clouds may form and sink, chemistry changes, infrared colors shift. It may pass through spectral classes similar to brown dwarfs, from warmer L-type appearances to cooler T-type, and perhaps Y-type characteristics. These letters may sound like a shelf labeling system invented during a very long afternoon, but they are useful. They tell astronomers about temperature, atmospheric chemistry, and the way light is absorbed and emitted. In the coldest cases, these objects may resemble giant planets more than stars, with atmospheres full of molecules, clouds, and weather patterns, only without a nearby sun adding light from above. If an object forms alone, does it have a surface? That depends on what kind of object it is. A gas giant mass body may have no solid surface you could stand on, just deeper and deeper layers of atmosphere until the pressure becomes crushing and the distinction between gas and fluid becomes strange. A lower mass rocky object formed in a disk and ejected would be different, with a surface of ice or rock. But star-like formation tends to produce gas-rich bodies, more like giant planets or brown dwarfs than Earth. This is one reason the origin question also shapes habitability speculation. A rocky rogue planet ejected from a system could have a solid surface and perhaps subsurface water. A star-like planetary mass object born from cloud collapse may be mostly hydrogen and helium, with no Earth-like surface at all. It may be fascinating, but not a frozen Earth. Again, the word planet can make our imagination jump too quickly toward continents and oceans. The reality may be more like a small, cold, failed ember with giant planet chemistry. Still, even if many born-alone objects are not Earth-like, they matter deeply for understanding how nature builds things. They reveal that the process of star formation may extend down into planetary masses. They suggest that the boundary between planets and brown dwarfs is not a wall but a slope. They also remind us that mass alone does not tell the full story. An object can weigh as much as a planet and be born like a star. Another can weigh as much as a planet and be born in a disk. A third can be born in a disk, thrown out early, and then spend nearly its entire life looking like it was always alone. Nature does not mind confusing our filing system. It has never once filled out a form correctly for our convenience. There is a gentle humility in this. For centuries, humans knew only the planets around our own sun. Then we discovered planets around other stars. Then we found planets in strange orbits, giant planets close to their stars, worlds around pulsars, planets in binary systems, super-Earths, mini-Neptunes, hot Jupiters, lava worlds, and planets that seem almost too fluffy or too dense for comfort. Now we find that some planetary mass objects may not orbit any star at all, and some may not have needed a star to be born. Each discovery widens the word planet until it becomes less like a fixed label and more like a question we keep asking. What counts as a world? What counts as a system? What counts as home? Born without a star is not the same as born without a universe. That may sound obvious, but it is worth lingering over. A free-floating planetary mass object still comes from cosmic material. Its hydrogen may have formed in the early universe. Its heavier elements were forged by earlier stars. Its dust grains may have passed through supernova shock waves, molecular clouds, and long cycles of galactic recycling. Even if it never had its own sun, it is still a child of stars in the older, deeper sense. Every atom heavier than helium carries a history of stellar interiors and explosions. So a planet-like object born alone is not truly parentless. Its parents are older generations of stars, the cloud that gathered their ashes, and the gravity that brought a small piece of that cloud together. If we could watch such an object forming, sped up over thousands or millions of years, it might begin as a slight thickening in a dark cloud. The surrounding gas would be cold, maybe only a few tens of degrees above absolute zero. Dust would block visible light from stars behind it. Gravity would pull inward. The clump would shrink. As it contracted, it would heat. Material might form a small disk as rotation flattened the infalling gas. Jets or outflows might appear if magnetic fields and accretion behaved as they do in larger star formation, though scaled down. The central object would glow faintly in infrared. It would never ignite like a star. It would not become a sun for future planets. It would simply condense, warm, feed for a while, then slowly run out of nearby material and cool. A world-like ember born in a dark nursery, carrying no sunrise in its future. The strange thing is that this story is both lonely and not lonely at all. It is lonely because the object does not gather a bright family of planets around a star. It is not lonely because it forms in a region full of other young objects, stars, brown dwarfs, disks, jets, gas and dust. Star-forming regions are busy places. They are not silent, empty rooms. They are more like cosmic construction sites, though much slower and with better lighting and infrared. A born-alone planetary mass object may begin near siblings, moving with a young association, sharing a common origin. Over time, the association spreads out. Stars drift apart. Brown dwarfs fade. Planetary mass objects cool. The whole family loosens into the galaxy, each member following its own path. After millions or billions of years, that once young object may truly seem isolated, but its isolation is the result of time and motion, not necessarily its beginning. This leads us back to the central uncertainty. When we find a rogue planet, we're often seeing the present clearly and the past dimly. Is it an ejected planet? A child of a disk that lost its star? Is it a tiny brown dwarf-like object, born directly from a cloud? Is it something in between, a forming embryo thrown out before it became larger? The answer may differ from object to object. Rogue planets are probably not one single family with one single origin. They may be a mixed population, some scattered from planetary systems, some formed like stars, some cut off while forming, some still carrying disks, some carrying moons, some old and frozen, some young and warm. The name Rogue Planet may gather them together, but beneath it is a whole set of histories, and perhaps that is why they are so interesting. A rogue planet is not only a lonely world, it is a clue to how flexible planet formation can be. It tells us that the galaxy is not built only from stars with neat systems around them. It contains unattached worlds, ambiguous objects, failed stars, planet-like bodies, and leftovers from young systems that became unstable. It contains objects that challenge the idea that planets must belong to suns. Some did belong, and were lost. Some may never have belonged at all. And both stories are useful, because both show that the universe makes worlds in more ways than one. Finding a world with no sunlight is a little like trying to find a silent fish in a black ocean by watching the ripples it leaves behind. A normal planet, if there is such a thing, usually gives astronomers at least one helpful clue. It orbits a star. It may pass in front of that star and block a tiny bit of light. It may tug on the star and make it wobble. It may reflect starlight, glow beside it, or leave a shadow in a disk of dust. The star, bright and generous and occasionally very inconvenient, acts like a lamp in the room. It makes the planet easier to notice, even if the star itself is often so bright that the planet is like a firefly near a lighthouse. But a rogue planet does not have that lamp. There is no parent star to dim, no regular orbit to time, no yearly rhythm to predict, no bright centre saying, "Look over here, one of my planets is hiding nearby." The planet is alone, faint, cold, and very good at not being found, which is rude. Scientifically speaking, though understandable if you have been drifting through interstellar space for millions of years. So astronomers had to become clever. They could not simply point a telescope at the night sky and expect rogue planets to appear as little round worlds, politely labelled and waiting for inspection. Most of them are too faint. Many are too cold. Some may be smaller than Earth, and a cold Earth-mass body wandering thousands of light-years away would be almost perfectly invisible in ordinary light. Even a giant rogue planet, something several times the mass of Jupiter, does not shine like a star. It may glow faintly in infrared when it is young, because it still holds heat from formation, but as it ages, that glow fades. The older it gets, the more it becomes a dark object among dark distances. It is not that it stops existing. It simply stops offering us easy evidence. The first major method for finding some of these objects is direct imaging, though direct can sound more straightforward than it really is. In this case, astronomers look for young, warm, planetary mass objects that glow in infrared light. They are not shining by nuclear fusion like stars. They are glowing because they are still cooling, still letting out the heat of their birth, like coals after a fire has gone quiet. Infrared telescopes are built to see this kind of warmth. They can pick up objects that are too dim and too cool for ordinary visible light searches. This is especially useful in young star-forming regions or young moving groups, where planetary mass objects have not yet had billions of years to cool into near invisibility. One of the most famous examples is PSOJ 318.5-22, a free-floating planetary mass object discovered using direct imaging. Its name may not exactly roll off the tongue like a beloved pet name, unless your beloved pet is a spreadsheet, but it is a wonderfully important object. PSOJ 318.5-22 does not orbit a parent star. It is young, relatively nearby in astronomical terms, and faintly glowing with leftover heat. NASA even turned it into one of its imaginative exoplanet travel posters, calling it a planet with no star, where the nightlife never ends. That phrase sounds playful, but beneath it is a serious scientific advantage. Because PSOJ 318.5-22 is not sitting right next to a dazzling star, astronomers can study its own light more cleanly. A planet orbiting close to a bright star can be very difficult to examine because the star overwhelms it. A free-floating world has no such glare beside it. It is faint, yes, but at least it is not faint while standing next to a cosmic floodlight. This is one of the unexpected gifts of rogue planets. They are hard to find, but once a young one is found, it can be easier to study in certain ways than a planet orbiting a bright star. Its light is its own. Astronomers can break that light into a spectrum, spreading it out by wavelength to look for the fingerprints of molecules in the atmosphere. Water vapour, methane, carbon monoxide, dusty clouds, surface gravity, temperature, all of these can leave subtle traces. A spectrum is not a photograph in the everyday sense. It is more like a barcode made by physics, and if you learn to read it, it can tell you what kind of atmosphere the object has, how hot it is, how young it may be, and whether it resembles young giant planets seen around stars. In the case of PSOJ 318.5-22, astronomers have used observations to study its atmosphere and variability, even mapping changes that suggest patchy clouds as it rotates. Imagine weather on a world without a sun, not weather driven by daylight, but by internal heat, rotation, chemistry, and cloud layers moving in a deep, dark atmosphere. Another important object is CFBDS, IRJ, 2149.47.2-0403-08.9, often shortened to CFBDS, IR2149-0403, which is very kind of scientists because otherwise we might all fall asleep before finishing the name, and not in the intentional way. ESO described it as an isolated planetary mass object and an especially interesting free-floating planet candidate, possibly associated with the AB Doradus moving group. A moving group is a loose collection of stars travelling together through space, likely born around the same time. If a faint object shares the motion of such a group, astronomers can estimate its age, and age is extremely important. Brightness alone does not tell mass clearly for these objects, because a young low-mass object can glow like an older, more massive one. Knowing the age helps break that confusion. If CFBD-SIR2-149-0403 is young enough, its brightness and temperature suggest a mass in the planetary range rather than the brown dwarf range. If the association is uncertain, its identity becomes more cautious. This is why scientists often call it a candidate, not because they are being difficult, but because the evidence has to be treated carefully. That caution is part of the story. Rogue planets sit in a difficult observational borderland. A small brown dwarf and a giant free-floating planet can look frustratingly similar. Both may be isolated. Both may glow faintly in infrared. Both may have cool atmospheres with molecules and clouds. If the mass is estimated rather than directly measured, and the age is uncertain, the label becomes delicate. This is why astronomers do not simply say, "There it is, definitely a planet. Case closed, kettle on." They compare motion, age, luminosity, temperature, spectra, and models. They ask whether the object is young enough to be planetary mass, whether it belongs to a known group, whether it could instead be a low-mass brown dwarf. It is slower than a dramatic discovery announcement, but much more trustworthy. Direct imaging, then, is like looking for warm embers in the dark. It works best for young, fairly massive rogue worlds that still glow. But what about older rogue planets? What about smaller ones? What about an Earth-mass wanderer that has cooled so much it gives off almost no detectable heat? For those, astronomers use one of the strangest and most elegant tools in observational astronomy: gravitational microlensing. Microlensing depends on a beautiful consequence of gravity. Mass bends space-time, and because light follows the curves of space-time, a massive object can bend light from something behind it. Usually we think of this with galaxies or black holes, but even a planet can do it. Just a little. If a rogue planet passes almost exactly in front of a distant background star from our point of view on Earth, the planet's gravity bends and focuses the star's light. The background star briefly appears brighter. The planet itself may remain completely unseen. It does not need to shine. It does not need to reflect. It reveals itself by acting as a tiny natural lens. This is wonderfully subtle. Somewhere in the crowded starfields toward the centre of the Milky Way, a background star sits quietly. A rogue planet drifts between that star and us. For a short time, the star brightens in a specific smooth pattern, then returns to normal. The whole event might last only hours, or even less for a very small planet. Then it is over. The alignment is gone. The planet continues on. Astronomers are left with a light curve, a record of brightness over time. and from that curve they try to infer the presence and possible mass of the unseen object. It is a little like knowing someone walked past your window at night because a candle flame bent and brightened for a moment. You never saw the person, you saw what their presence did to the light. One of the famous microlensing examples is OGLE-2016-BLG-1928. This event was extremely brief, with a brightening timescale of only about 41.5 minutes. That short duration is important because in microlensing, smaller lensing objects tend to produce shorter events. The observation suggested a very low-mass object, possibly around a fraction of Earth's mass if located in the galactic disk, and either free-floating or separated from any host star by a wide distance. It is not the kind of rogue planet we can point to in an image and admire. There is no pretty photograph of a round world floating alone. Instead, there is a brief mathematical signature in the brightness of a background star. But that is exactly why it matters. It shows that microlensing can reach down towards smaller rogue planet candidates, the kind that direct imaging would miss almost completely. OGLE, the optical gravitational lensing experiment, has spent years watching dense star fields for these tiny brightenings. The Korea Microlensing Telescope Network, often called KSMT-NET, also watches the sky with a network of telescopes that can follow events from different longitudes on Earth. This matters because a microlensing event can be short. A rogue planet does not send a polite calendar invitation. It does not say, "I will pass in front of this star on Tuesday afternoons, please prepare snacks." It simply aligns, brightens the background star and moves on. If your telescope is under clouds, or if the star field is below the horizon, the event may be missed. Networks of telescopes improve the chances, passing the watch from one part of Earth to another as the planet's gravitational shadow, so to speak, crosses our line of sight. Microlensing is especially powerful because it does not require light from the planet. A cold, dark, old, low-mass planet can still bend light. In that sense, gravity becomes the planet's announcement. But microlensing has a downside. Most events happen only once. The alignment will not repeat on a convenient schedule. A planet orbiting a star may transit again and again, letting astronomers collect more data. A microlensing rogue planet may give only a single signal, and then it is gone from practical reach. That means every data point matters. The shape, duration, and brightness of the event must be captured quickly and carefully. It also means that some uncertainties remain. Is the lens truly free-floating, or is it orbiting a distant star that is too far away to reveal itself in the event? Sometimes astronomers can rule out nearby stellar companions within certain distances. Sometimes they cannot. Science here is not a magic wand. It is a careful scale, weighing possibilities in the dark. A third way astronomers find rogue planets is by surveying young star-forming regions with sensitive infrared instruments. This overlaps with direct imaging, but on a population scale. Instead of looking for one known object, astronomers map entire nurseries, searching for faint red sources that are too cool and too low mass to be stars. The James Webb Space Telescope is especially good at this, because it sees infrared light with extraordinary sensitivity. Young rogue worlds in places like NGC 1333, a star-forming region in the Perseus molecular cloud, can still be warm enough to detect. Some recent Webb observations have identified multiple free-floating planetary mass candidates in such regions, helping scientists study where the lower edge of star-like formation may lie. These objects are not always given catchy individual names in public summaries, but the surveys are crucial. They help astronomers move from "we found a strange object" to "we can start counting how many strange objects there are." Counting is not glamorous, but it is powerful. One rogue planet is a curiosity, 10 are a pattern, hundreds can reshape theory. If young star-forming regions contain many free-floating planetary mass objects, then perhaps some form like stars, directly from collapsing gas clouds. If microlensing surveys find huge numbers of low-mass objects in the older galaxy, that may support the idea that planetary systems eject many small worlds. The method matters because each method sees a different kind of rogue planet. Direct imaging favours young, warm, massive objects. Microlensing can reveal cold, dark, low-mass objects, but often only for a brief moment. Infrared cluster surveys find young populations, especially where ages can be estimated. No single technique gives the full picture. Astronomers are assembling the rogue planet population from fragments, like trying to understand a whole forest by studying warm seedlings, drifting leaves, and footprints in snow. There is also the method of proper motion, which sounds plain but is quietly important. If an object is nearby enough, astronomers can watch its position shift slightly against the background stars over time. This motion across the sky can show whether it belongs to a nearby moving group or star-forming region. For objects like CFB-DSIR2 149-0403, proper motion was a key clue in assessing possible membership in the AB Doradus moving group. Proper motion is not dramatic. It may require comparing images taken years apart, but it tells us whether a faint point of light is moving with a known family of stars or merely passing in the same direction by chance. In a universe where so many things are far away and faint, motion is identity. It says, this object is not just a speck, it has a path. Spectroscopy then turns that path into a physical portrait. By splitting the light of a faint rogue planet candidate, astronomers can estimate temperature and atmospheric composition. Low surface gravity can indicate youth, because young giant planets and brown dwarfs are still relatively puffed up compared with older compact objects. Molecules absorb specific wavelengths. Clouds change the shape of the spectrum. Methane may appear in cooler atmospheres. Dusty clouds may redden the light. These are not simple observations. The signals are faint. Models are needed. Different combinations of mass, age, cloud properties, and chemistry can mimic one another. Still, spectroscopy is one of the best ways to turn a faint dot into a world with conditions. Chaowan 107-7626 shows another fascinating possibility. Sometimes a rogue planet can reveal itself not only by glowing, but by feeding. This young, free-floating planetary mass object, located in the Chamaeleon region, is surrounded by a disk of gas and dust, and has been observed accreting material. In 2025, astronomers reported a dramatic growth spurt, with material falling onto it at a record rate for a planetary mass object. That is extraordinary, because accretion bursts are usually associated with young stars. Here, a rogue planet-like body behaved in a way that blurs the line between planet formation and star formation. For our purposes, it also shows another way these objects can be studied. A disk, emission lines, changes in brightness, and chemical signatures can all reveal a young rogue world in the act of becoming. Not every rogue planet is an old frozen wanderer. Some are still in their messy youth, still pulling in material, still surrounded by the leftovers of their birth. This is the opposite of how we usually imagine planets. We tend to picture planets as finished objects, already shaped, already orbiting, already arranged in tidy systems. But young rogue planets can still be active. They can have disks, they can accrete, they can flare in brightness. They can show water vapour or hydrocarbons in surrounding material. They can behave in some ways like miniature versions of young stars. This does not mean they are stars. It means the process of forming objects across the star-planet boundary may share more physics than we once expected. Gravity pulls material inward. Disks form because rotating material cannot fall straight in. Magnetic fields may guide flows. Heat and light emerge from infalling gas. The same broad ingredients appear, scaled down to planetary masses. The universe is rather fond of repeating themes at different sizes, like a musician playing the same melody on a grand piano, then on a music box. Future searches should make this picture much clearer. NASA's Nancy Grace Roman Space Telescope is designed to carry out a large microlensing survey, watching dense star fields with the steadiness needed to catch many brief events. Because Roman observes from space, above Earth's atmosphere, it should see with greater stability and continuity than ground-based surveys alone. It may detect hundreds of rogue planets, including objects with masses much smaller than Jupiter. That matters because the biggest uncertainty is not whether rogue planets exist. They do. The big question is how many exist at different masses. Are Jupiter mass rogue planets common? Are Earth mass ones common? Are Mars mass ones out there in enormous numbers, little frozen seeds scattered by chaotic young systems? The answers will tell us how rough planet formation really is. Euclid, Webb, Roman, ground-based microlensing networks, large infrared surveys and future giant telescopes all contribute different pieces. Euclid can image wide regions with great sharpness. Webb can study faint young objects in infrared. Roman can watch for microlensing flashes. The extremely large telescope and other future observatories may directly study atmospheres of faint objects in even more detail. It is a slow transformation. Rogue planets are moving from speculation to catalogue entries, from catalogue entries to populations, and from populations to formation histories. The dark is becoming searchable. Still, there is something humbling about the fact that many rogue planets will remain hard to know individually. A tiny microlensing event might tell us that a planet passed through the line of sight, but not give us a portrait. A faint infrared object might let us study atmosphere and temperature, but leave its origin uncertain. A young accreting object like Char 1107-7626 may show us formation in progress, but not necessarily tell us how common such behavior is. Each detection is partial. Each method has blind spots. Astronomers have to combine them carefully, comparing direct imaging with microlensing, young regions with older field populations, spectra with motion, models with statistics, and perhaps that is fitting. A rogue planet is a world without an obvious light, so we should not be surprised that finding one requires indirect thinking. We find it by warmth left over from birth. We find it by gravity bending a background star. We find it by its motion with a young stellar family. We find it by the chemistry of a faint atmosphere. We find it by a disk still feeding it in the dark. PSOJ 318.5-22 gives us nearby young example, whose own faint glow can be studied without a parent star's glare. CFBDS-RJ 214947.2-040308.9 shows how motion, age, and group membership can turn a faint infrared object into a serious free-floating planet candidate. OGLE-2016-BLG-1928 shows how a planet-like object can announce itself through a brightening that lasts less than an hour. Char 1107-7626 shows that some rogue planets may still be forming, still growing, still behaving like little cosmic engines rather than quiet finished worlds. So when you next imagine astronomers searching for planets, do not picture only bright stars with neat shadows passing across them. Picture also a telescope staring patiently at a crowded patch of the Milky Way, waiting for one star among millions to brighten for a few minutes. Picture an infrared survey of a young nebula, where faint warm dots hide among newborn stars and dusty filaments. Picture a spectrum stretched into colours so carefully that molecules reveal themselves as missing light. Picture scientists comparing images taken years apart, watching a tiny point crawl across the sky by almost imperceptible amounts. This is how you find a world with no sunlight, not by expecting it to shine, but by noticing every small way it still touches the universe around it. And once astronomers find such a world, the question naturally changes. It is no longer only, how did we notice it? It becomes, what is that world actually like? What happens on a planet that has no sunrise, no summer, no daylight, and perhaps no familiar sky? Does it freeze into silence, or can its interior keep secrets warm beneath layers of ice and gas? Once a planet has no star to warm it, the story becomes quieter, but not simpler. It is tempting to imagine a rogue planet as a dead frozen ball, a cosmic stone left in a freezer so large that even the word cold feels underdressed. And for many rogue planets, especially small rocky ones with thin atmospheres, that may not be far from the truth at the surface. Without sunlight, the ground loses heat into space. Oceans freeze from above. Clouds, if they exist, may change into frost or snow. The familiar weather engine of a sunlit planet slows down or stops. There is no warm afternoon, no bright equator. No spring returning after winter, no sunrise arriving with the casual confidence of a star that has been doing this for billions of years. A starless world has to live on what it can keep, what it can make, and what it can hide. The first thing to understand is that planets are not warmed only from the outside. Earth feels like a sun-powered world because at the surface, it mostly is. The sun drives our climate, evaporates our oceans, grows our forests, powers our winds, and gives us the lovely illusion that planets are basically outdoor places with weather. But Earth also has heat inside it. Deep under your feet, the planet is warm because of leftover heat from formation and the slow decay of radioactive elements in the rocks. This internal heat is much weaker than sunlight at the surface, but it is steady and important. It keeps Earth geologically alive. It helps drive plate tectonics, fuels volcanoes, warms deep rock, and supports hydrothermal vents on the ocean floor. These vents are particularly interesting because they show that energy can support ecosystems without sunlight. Life there does not depend on leaves and sunshine. It depends on chemistry, heat and water moving through rock. Now move that idea into interstellar space. Take a rocky planet and remove its star. The surface becomes cold very quickly by planetary standards, though quickly here still means something that can stretch over years, centuries or longer depending on the atmosphere and oceans, but the interior does not instantly freeze. Rock is a good insulator. Ice can be an even better one in some conditions. A planet with enough internal heat and enough insulation may keep warmth trapped below the surface long after the sky has gone dark. This is one of the reasons rogue planets are not scientifically boring. Their surfaces may be silent, but their interiors can still have stories to tell. A frozen crust might sit above a deep ocean. A thick atmosphere might trap heat. A large moon might be flexed by gravity and warmed from within. The planet may look lifeless from the outside while still holding motion, chemistry and slow heat below. The surface temperature of a rogue planet depends on many things, and that is where the simple picture begins to wobble. How massive is the planet? Is it rocky or gaseous? How old is it? Did it form recently, still glowing with heat, or has it been cooling for billions of years? Does it have an atmosphere? If so, what is that atmosphere made of? Is the atmosphere thin and easily frozen, or thick and insulating? Does the planet have a large moon or several moons creating tidal heating? Does it have radioactive elements in its interior? Did it begin with oceans? Did it lose them before it was ejected? These details matter. A rogue planet is not one kind of world. It is a situation. The situation is no nearby star. What happens after that depends on the planet. For a small rocky rogue planet with no thick atmosphere, the outcome would be harsh. Space is cold, not because cold is a substance floating around out there, but because there is almost nothing to give heat back. A planet radiates energy away as infrared light. If sunlight is not replacing that lost energy, the surface temperature falls. On Earth, the sun provides the overwhelming majority of surface heating. Without it, the atmosphere and oceans would begin to cool dramatically. The top of the ocean would freeze first. Ice would spread. Snow would not melt. Carbon dioxide could freeze out under certain conditions. Nitrogen and oxygen might remain gases for a while depending on temperature and pressure, but if the cooling became extreme enough, even parts of the atmosphere could collapse onto the surface as frost. The planet would become darker, quieter, and harder to recognize. And yet, ice can protect what lies beneath. This may sound odd because we often think of ice as the sign that warmth is gone, but ice is also an insulating blanket. On Earth, lakes can freeze on top while liquid water remains below, allowing fish and other organisms to survive the winter underneath. Now stretch that idea to a planetary scale. If a rogue world had an ocean and enough internal heat, the surface could freeze into a thick shell while liquid water remained below. The thicker the ice, the more difficult it becomes for heat to escape. Eventually, a balance might form between heat rising from the interior and heat leaking out through the ice. The surface would be extremely cold, but beneath the crust, the ocean could remain liquid. This would not be a beach holiday. There would be no palm trees, no pleasant sunset, and frankly, the hotel reviews would be poor. But as a physical possibility, it is fascinating. The energy in such an ocean would not come from sunlight, it would come from the planet itself. Radioactive decay inside the rocky mantle would release heat slowly. Leftover heat from formation would continue to leak outward. If the planet had plate tectonics or some form of internal circulation, water might interact with hot rock, producing chemical gradients. Hydrothermal vents could exist on the ocean floor, releasing minerals and heat. On Earth, similar environments support ecosystems that do not need sunlight directly. They rely on chemical energy, especially from reactions involving compounds like hydrogen sulfide or methane. A rogue planet with a subsurface ocean might have similar chemical possibilities if the right ingredients were present. This does not mean life would definitely exist. Life is not something we should sprinkle across every interesting environment like cosmic cinnamon. But it means that darkness alone does not automatically remove every source of usable energy. A thick atmosphere changes the story in another way. Atmospheres trap heat by absorbing and re-emitting infrared radiation. On Earth, greenhouse gases make the surface much warmer than it would be without an atmosphere. On a rogue planet, there is no sunlight to trap, but there is still internal heat coming from below. If a planet has a very thick atmosphere, especially one rich in hydrogen, it might trap that internal heat remarkably well. Hydrogen is not a strong greenhouse gas in the same simple way that carbon dioxide or water vapor often are. But under high pressures, hydrogen molecules can absorb infrared radiation through collision-induced absorption. In plain language, when hydrogen molecules bump into each other in a dense atmosphere, they can briefly behave in ways that let them absorb heat radiation more effectively. It is a little like a crowd that becomes better at catching passing beach balls simply because everyone is packed closer together, though admittedly with more quantum mechanics and fewer sandals. A rogue planet wrapped in a dense hydrogen atmosphere could, under the right conditions, keep its surface much warmer than a bare rock would. Some theoretical studies have suggested that a free-floating rocky planet with a thick enough hydrogen-helium atmosphere might maintain liquid water at the surface for long periods, even without a star. That is an astonishing possibility, but it comes with many conditions. The planet must hold on to that atmosphere. It must have enough internal heat. The pressure at the surface might be enormous. The atmosphere might be deep and crushing compared with Earth's. The sky would not be blue in the familiar way, because there would be no bright sun scattering through it. It might be dark, dense and strange, with heat trapped under a heavy gaseous blanket. So when we imagine such a world, we should not imagine Earth simply moved into the dark with a thicker coat. It would be its own kind of place, perhaps warm enough in principle, but not necessarily comfortable, familiar, or easy to visit without becoming a very flat explorer. Gas giant rogue planets have a different kind of cold life. A planet like Jupiter is not just a ball of frozen gas waiting for sunlight. Jupiter radiates more energy than it receives from the sun, because it still has internal heat from its formation and slow gravitational contraction. A rogue gas giant, especially a young one, could continue to glow in infrared for millions or even billions of years as it cools. It may have storms driven by internal heat rather than sunlight. Its atmosphere could be full of bands, clouds, turbulent flows, and chemistry shaped by pressure and temperature. Without a nearby star, there would be no sunlit side and no night side. The entire planet would be night by our standards, but not necessarily still. Deep inside, heat would rise, the planet would convect, clouds would form and shift. Lightning might flash inside the dark atmosphere, briefly lighting cloud layers that no sunrise has ever touched. For young rogue gas giants, this internal heat is also what helps astronomers find them. They glow in infrared because they are still cooling, and that glow can reveal them in young star-forming regions. But that glow fades with time. A billion-year-old rogue giant is much dimmer than a 10-million-year-old one. A very old one may be extremely cold at its cloud tops, perhaps only tens of degrees above absolute zero depending on its mass and history. Yet even then, the interior can remain warm at great depth. Giant planets are layered by pressure. Go down into the atmosphere, and pressure and temperature rise. There may be no solid surface, just gas becoming dense fluid, hydrogen behaving strangely, and deeper regions where conditions become far beyond anything humans can casually imagine over a cup of tea. If a rogue gas giant has no star, its outside can be deeply cold while its inside remains an enormous reservoir of trapped energy. Moons make the energy story even more interesting. A rogue planet may not be alone if it escaped its system with moons still attached. Whether moons survive depends on how violent the ejection was and how tightly the moons orbit. A faraway moon could be stripped away during close encounters, but a close moon may remain bound. If a rogue planet carries several moons, their gravity can tug on one another and keep their orbits slightly stretched. A moon in an eccentric orbit does not feel the same gravitational pull at every point in its path. It flexes. Its interior is squeezed and released, and that flexing generates heat. This is tidal heating. In our solar system, Io is heated so strongly by Jupiter's tides that it is covered in volcanoes. Europa and Enceladus are icy moons, where tidal heating helps keep subsurface oceans possible. Around a rogue giant planet, moons could be warmed by similar processes even without a sun. That is a remarkable thought. A starless planet might carry a smaller world that has more internal activity than the planet's distance from any star would suggest. The moon's sky would still be dark. The rogue giant might loom overhead as a massive black or faintly glowing disk, perhaps lit only by its own infrared heat and the background of stars. There would be no bright sunlight reflecting from it. But below the moon's icy crust, tidal heat could support a liquid ocean. Chemical reactions between water and rock could provide energy. Hydrothermal vents might exist. Again, this is not a claim that such places are inhabited. It is a reminder that a star is only one way to power a world. Gravity can also be an engine. So can radioactive decay. So can the slow settling of a giant planet's interior. The universe does not rely on one plug socket. A rogue planet's weather, if it has an atmosphere, would also be shaped differently from weather on Earth. On our planet, the sun heats the equator more than the poles. Day and night create temperature differences. Land and ocean warm at different rates. Seasons shift the balance through the year. All of this helps drive winds, storms, clouds, and rain. A rogue planet lacks the main external pattern. There is no solar heating from one direction. That does not mean no circulation, but it means circulation comes from internal heat, rotation, atmospheric chemistry, and perhaps uneven surface or interior heat flow. A thick atmosphere over a rocky rogue planet might move heat from warmer lower layers to colder upper layers. Clouds could form from gases freezing or condensing at different heights. Snow might fall made not of water, but methane, nitrogen, carbon monoxide, or other compounds, depending on temperature. On some worlds, the weather might be less like Earth's rain, and more like chemistry deciding where it can no longer stay gaseous. The sky would be one of the strangest parts. On a bare, rocky, rogue planet, the sky might be black and full of stars if there is no thick atmosphere. If there is an atmosphere, the stars may be dimmed or hidden by clouds and haze. Without a sun, there would be no blue daylight, no red sunset, no bright horizon. If the planet has auroras, perhaps from a magnetic field interacting with charged particles in interstellar space, the sky might glow faintly at times. If the planet has lightning in its clouds, there might be sudden internal flashes. If it is a young giant still warm in infrared, human eyes might see almost nothing, while infrared instruments would reveal a glowing world. This is one of those places where our senses are not enough. To us, it is dark. To the right telescope, it is still radiating, still losing heat, still speaking in wavelengths we cannot see. The rate at which a rogue planet cools depends strongly on its size. Bigger worlds hold heat better because they have more volume compared with their surface area. A small object loses heat quickly. A large planet can keep internal warmth for a very long time. This is why small moons and asteroids often become geologically quiet, while larger planets and moons can stay active longer. A super-Earth rogue planet, more massive than Earth, might retain heat better than Earth would. It may have stronger gravity, a thicker atmosphere, and more internal pressure. If it had water, a thick ice shell could form, but internal heat might keep deeper layers liquid. If it had a hydrogen atmosphere, the pressure and insulation could become significant. The same mass that makes a world harder to escape also helps it hold on to heat and atmosphere. In the dark, size can be survival. But there are limits. Heat leaks. Radioactive elements decay and become less powerful over time. Formation heat fades. Atmospheres can be lost, frozen, or stripped. A rogue planet is not magically warm. It is fighting a very long cooling process. The cold of interstellar space is patient. Given enough time, many rogue worlds will become extremely cold at their surfaces, and smaller ones may become frozen throughout, except perhaps for pockets of residual heat deep inside. The question is not whether the dark wins eventually in many cases. The question is how long the planet can delay it, where warmth can remain, and whether any environments stay active long enough to matter. In planetary science, timescale is everything. A frozen surface after 1,000 years is different from a hidden ocean lasting billions of years. A brief warm youth is different from long-term stability. This is where rogue planets become a kind of lesson in energy accounting. Every planet has an energy budget. Energy comes in, energy goes out, and the balance determines temperature. For Earth, sunlight is the large incoming term. For a rogue planet, that term is almost gone. The remaining sources are internal: heat from formation, heat from radioactive decay, heat from tidal flexing if there are moons or companions, heat from gravitational contraction in giant planets, perhaps chemical energy in certain environments. Against these sources is radiation to space, the steady leaking away of heat as infrared light. An atmosphere or ice layer can slow that leak, but it cannot stop it completely. The life of a rogue planet is therefore the life of stored warmth trying to escape. There is something deeply quiet about that. We often think of planets in terms of light. Mars is red in the sun. Venus shines in our evening sky. Jupiter gleams. Saturn glows pale and steady. Earth is blue and white because sunlight scatters through air and reflects from oceans and clouds. A rogue planet removes that familiar lighting and asks us to think in terms of heat instead. Not brightness, but temperature. Not daylight, but insulation. Not seasons, but cooling curves. Not sunrises, but internal gradients. It is still a world, but one understood by thermodynamics more than by scenery. And yet scenery may still exist if anyone could see it. Ice plains under star fields, frozen atmospheres lying as frost, dark clouds rolling above a hydrogen-covered surface, a gas giant storms churning invisibly to human eyes, a moon's cracked ice shell above a hidden sea. These are not warm places in the ordinary sense, but they are not nothing. A rogue Earth is especially useful to imagine because it begins from something familiar. If Earth were somehow ejected from the solar system, the sun would slowly shrink behind us. Days would lose their meaning as sunlight faded. Plants would die as photosynthesis failed. Surface temperatures would plunge. The oceans would freeze from the top down, but the deepest oceans might remain liquid for a long time beneath thick ice, warmed from below by geothermal heat. The atmosphere would change as gases condensed or remained depending on their freezing points and pressure. Human civilization on the surface would not survive without extreme technology, and even then only by living off stored nuclear, geothermal or artificial energy. But microbes deep underground or around hydrothermal vents might be more insulated from the catastrophe. This is not a comforting survival plan, more of a cosmic reminder not to take the sun for granted. The sun is not merely a bright object in the sky. It is the reason our surface world is awake. For a rogue planet born without a star, the story would be different. It may never have had oceans warmed by sunlight. It may never have had a surface climate in the Earth-like sense. If it is a gas-rich planetary mass object, it may have spent its whole life cooling from a warm beginning, its atmosphere evolving as temperatures dropped. If it formed with a small disk and moons, those moons might become the more interesting places. If it is a rocky object ejected early from a young system, it may have formed with volatiles and then carried them into the dark. If it left later, after oceans or atmosphere developed, it may preserve some of that history under ice. Rogue planets are not one story repeated many times. They are many different cooling histories wearing the same dark cloak. And this brings us to a useful correction. Cold does not mean simple. Cold worlds can have layers, chemistry, pressure, motion, and hidden reservoirs. Pluto is cold, yet geologically interesting. Europa is icy, yet may hide an ocean. Titan is frigid, yet has weather, lakes, dunes, and organic chemistry. These worlds still orbit the sun, of course, and receive some sunlight, but they remind us that low temperature does not erase complexity. A rogue planet pushes that idea farther. It asks how far complexity can go without a star. Can an atmosphere stay thick enough? Can an ocean stay liquid enough? Can chemistry stay active enough? Can moons keep flexing enough? Can a planet's own heat be enough to maintain a private interior world beneath a frozen exterior? A calm way to think of it is this. A sunlit planet lives with an open fireplace in the sky. A rogue planet lives with embers under the floor. The fireplace is bright, obvious, and warming from above. The embers are hidden, weaker, and easier to miss. But in a well-insulated house, embers can matter. They can keep a room from freezing completely. They can preserve warmth in places the wind cannot reach. On a rogue planet, the ice, atmosphere, rock, and ocean are the walls of that house. Whether the warmth lasts depends on how thick those walls are, how strong the embers remain, and how long the night has already lasted. So the cold, quiet life of a rogue planet is not necessarily a blank life. It may be a long cooling, a deep storing, a hiding of energy beneath layers that no sunrise ever touches. It may be a gas giant glowing faintly in infrared, its storms moving in darkness. It may be a rocky world sealed under ice, with heat rising slowly from a restless interior. It may be a moon system where tidal flexing keeps one small ocean alive around a planet that no star has claimed. It may be a frozen body so cold and still that almost nothing changes for billions of years. All of these possibilities belong to the same broad idea, a world without a sun living on its remaining heat. And once we understand that heat can be hidden, the next question becomes almost unavoidable. If a rogue planet can keep warmth beneath ice, and if water can remain liquid in protected places, could there be an ocean down there, sealed away from starlight, warmed by the planet's own interior, quiet under a roof of frozen darkness? That question sounds almost too hopeful at first, doesn't it? A planet with no sun, no daylight, no warm seasons, no star hanging above it, and yet somewhere beneath all that darkness, an ocean might still be waiting. Not a sparkling blue ocean under a bright sky, not waves catching sunlight, not beaches, tides, clouds, and gulls making a dramatic nuisance of themselves. This would be a hidden ocean, sealed under ice, pressed under miles of frozen crust, warmed not from above but from below. It would be an ocean that never sees the sky, an ocean with no sunrise moving across it, no moon glittering on its surface, perhaps no surface in the ordinary sense at all. And yet, physically, it is not impossible. In fact, once you begin to think carefully about heat, insulation, pressure, and the strange persistence of water, the idea becomes less like fantasy and more like one of those quiet possibilities the universe leaves tucked in a drawer. The first thing a rogue planet needs for an ocean is, of course, water. That sounds obvious, but in planetary science, obvious things often come with footnotes. Water can be delivered during formation, trapped in minerals, gathered as ice, held in the outer parts of a young planetary system, or included in the building blocks that made the planet in the first place. In our own solar system, water is not rare. Earth has oceans on the surface. Europa likely has a salty ocean beneath its icy crust. Enceladus sprays water-rich plumes into space from a hidden sea. Ganymede and Callisto may have deep internal oceans. Even small icy worlds can hold surprising amounts of water when the conditions are right. So if a rocky or icy planet formed beyond the snowline of its original system, where cold temperatures allowed water ice to be abundant, it might begin life with plenty of water locked into its structure. If that planet were later ejected, it would carry that water into interstellar space like a packed lunch for a journey no one planned. The second thing it needs is heat, and this is where the story becomes more interesting. Without a star, surface heat quickly disappears. A bare ocean exposed to interstellar space would freeze from the top downward. The air above it, if any remained, would cool. Snow and frost would accumulate. The surface would turn hard, white, and silent. But freezing from the top does not necessarily freeze the whole ocean at once. Ice is less dense than liquid water, so it floats, forming a lid. That lid can grow thicker and thicker as heat escapes upward, but it also acts as insulation. The thicker the ice becomes, the more slowly heat can leave the liquid water below. This is why a lake on Earth can freeze at the surface while fish still swim underneath. Now enlarge that idea to the size of a planet, remove the sunlight, add internal heat rising from below, and you begin to see the possibility. The ice is not only a sign of cold, it is also a roof. Under that roof, the ocean's fate depends on the balance between heat escaping upward and heat supplied from below. If the planet's interior produces enough heat, the lower part of the ice shell may stay warm enough to melt, maintaining a liquid ocean beneath. That heat can come from several places. Some is left over from formation, when the planet assembled from colliding material and gravitational energy turned into heat. Some comes from radioactive decay, the slow breakdown of elements inside the rocks. On Earth, radioactive decay helps keep the mantle warm and the planet geologically active. A rogue planet with a rocky interior can have the same kind of heat source, though the amount depends on its composition and age. A young rogue planet may have more leftover heat. A more massive rogue planet may retain heat longer. A world with more radioactive elements may stay warm inside for longer still. The surface may be unimaginably cold, but the deep interior may not have received the memo. A planet's size matters greatly. Small worlds lose heat more quickly because they have more surface area compared with their volume. A small, icy body can freeze through more easily. A larger rocky world, especially one more massive than Earth, can hold heat for far longer. This is one reason scientists have imagined so-called Steppenwolf planets, rogue worlds with enough mass, water and insulation to keep a liquid ocean beneath ice for billions of years. The name is rather good, because it suggests an animal moving alone across a cold landscape, but the science underneath is serious. A planet a few times Earth's mass, with an Earth-like rocky interior and a thick enough water ice layer, could in theory trap geothermal heat below the surface and maintain a subglacial ocean. If the planet had more water than Earth, or an additional frozen atmospheric layer adding insulation above the ice, even a smaller world might manage it under the right circumstances. This does not mean every rogue planet has an ocean. Most probably do not, or at least we should not assume they do. A dry rocky planet thrown out from close to its star may have little water to preserve. A small icy body may freeze solid. A gas giant may have no ocean surface in the familiar sense, though it may host moons with oceans. A planet with too little internal heat may lose the battle against the cold. A planet with too much pressure at depth may turn some of its water into high-pressure ice phases, which are not the same as ordinary surface ice. That last point is especially important and wonderfully strange. Ice is not just one thing. Under high pressure, water can freeze into exotic forms of ice, even at temperatures where ordinary ice would melt. Deep inside large icy planets, high-pressure ice can form beneath liquid layers. This means an ocean might be sandwiched between an upper ice shell and lower high-pressure ice, separated from the rocky sea floor. That matters because contact with rock can provide chemical energy, minerals, and reactions important for habitability. A hidden ocean is more interesting from a life perspective if it touches rock. On Earth, the deep ocean floor is not simply a cold bottom. It is a place where water can circulate through cracks in the crust, heat up, react with minerals, and return through hydrothermal vents. These vents release warm, chemically rich fluids into the ocean. Around them, ecosystems thrive without sunlight. Microbes use chemical reactions for energy, and larger organisms depend on those microbes. It is one of the great lessons of modern biology. Sunlight is not the only way to power life. Life at hydrothermal vents does not care whether it is noon above the waves. It cares whether there is water, chemistry, heat, and time. A rogue planet with a subsurface ocean in contact with a rocky seafloor could, in principle, have similar energy sources. Water moving through warm rock could create hydrogen and other chemical ingredients. Minerals could dissolve. Chemical gradients could form. These gradients are like tiny batteries for microbes, if life is there to use them. Europa and Enceladus are useful examples, not because they are rogue planets, but because they show that oceans can exist under ice in cold places. Europa orbits Jupiter, and it receives some sunlight, but sunlight is not what keeps its ocean interesting. Tidal heating from Jupiter's gravity, along with internal processes, helps maintain conditions beneath the ice. Enceladus is smaller, yet it has a global subsurface ocean and sprays water-rich plumes from cracks near its south pole. Cassini detected signs suggesting hydrothermal activity and chemical energy in that hidden ocean. These moons are like nearby demonstrations that ice-covered oceans are not just theoretical decoration. They exist, or are strongly supported by evidence, in our own solar system. A rogue planet would be different, especially without a giant planet nearby to provide tidal heating, unless it had moons or companions of its own. But the basic lesson carries over. Ice can hide water. Internal heat can matter. Rock-water chemistry can create possibilities that sunlight never sees. For a rogue planet, the most straightforward ocean would be beneath a thick ice shell. Imagine a planet somewhat larger than Earth, rich in water, drifting through interstellar space. Its surface is colder than any winter humans have ever known. The sky is black. Stars shine above with no sun to wash them out. The surface ice may be kilometers thick, perhaps tens of kilometers, perhaps much more depending on the heat flow and water content. There may be no weather in the familiar sense, only slow frost, cracking, settling, and the long movement of ice over geological time. But far below, where pressure and interior heat raise the temperature, ice gives way to liquid water. The ocean may be dark, salty, and deep. It may not have waves, because there is no open surface and no wind. It may circulate slowly because of heat from below and cooling above. Warm water might rise near hydrothermal regions. Cold water might sink elsewhere. The whole ocean could turn over on timescales that make human history look like a sneeze. Salt matters here. Pure water freezes at 0 degrees Celsius under Earth's surface pressure, but salty water freezes at lower temperatures. The salts and other dissolved substances in an ocean can make it easier for water to remain liquid. This is one reason ocean worlds can stay liquid under conditions that would seem too cold at first glance. Antifreeze chemistry, if we may call it that, without picturing a planet pouring something suspicious into its own radiator, can help. Ammonia, salts, and other compounds can lower freezing points. In some icy moons, ammonia may play a role in keeping internal liquids stable at lower temperatures. The exact chemistry of a rogue planet's ocean would depend on its formation, rock composition, and history. It could be salty like Earth's ocean, richer in ammonia, loaded with dissolved gases, or chemically alien in ways that would make a fish extremely confused. Pressure also shapes the ocean. Beneath a thick ice shell, pressure increases with depth. On a more massive planet, gravity may be stronger, increasing pressure even faster. This affects melting, ice phases, and the structure of the ocean. In some cases, pressure helps keep water liquid. In others, it creates high-pressure ice at the bottom. A deep ocean on a large water-rich planet might not touch rock directly because high-pressure ice forms between the ocean and the rocky interior. That could make chemical exchange harder. Without contact with rock, the ocean may have fewer energy sources useful for life. It could still have chemistry, but it may lack the active seafloor reactions that make hydrothermal vents so promising. This is one of those details that reminds us habitability is not just water equals life. Water is important, yes, but water also needs energy, nutrients, stability, and a way to keep chemistry moving. A rogue planet with a thick hydrogen atmosphere could keep water in a different way. Instead of an ocean hidden under ice, it might maintain liquid water at or near the surface beneath a dense insulating atmosphere. This idea is more exotic and depends on conditions being just right. A hydrogen-rich atmosphere can trap internal heat very effectively if it is thick enough. The planet's surface might remain above the freezing point of water, even without sunlight. But the atmosphere would likely be massive and high pressure. Standing there would not feel like standing beside a quiet lake under stars. It might feel, if one could survive it, like being at the bottom of an immense, dark, atmospheric ocean. The sky might be opaque. Pressure could be enormous. The water might exist under conditions more like the deep ocean floor than a beach. Still, from a physics standpoint, it shows another route. Ice is not the only possible blanket. Gas can be a blanket too. The survival of an ocean also depends on time. A rogue planet ejected yesterday, cosmically speaking, might keep oceans for a while even if it eventually freezes. A rogue planet drifting for billions of years needs a long-term heat balance. Geothermal heat declines slowly but does decline. Radioactive isotopes decay. The interior cools. Ice thickens as less heat reaches the surface. If the ice becomes too thick, the ocean may shrink. If the heat flow drops too low, the ocean may freeze completely. Larger mass helps. More water can help by creating a thicker insulating layer, though too much water can create high-pressure ice complications. A frozen atmosphere lying on top of the ice, made perhaps of nitrogen, carbon dioxide or other gases, might add insulation. Every layer changes the outcome. A rogue planet is not simply hot or cold. It is a stack of materials negotiating with heat. There is also tidal heating, if the rogue planet has companions. A lone rocky rogue planet has to rely mostly on its own internal heat. But a rogue gas giant with moons, or a rogue planet in a binary pair with another planetary mass object, can generate tidal energy. A moon in a slightly elliptical orbit is squeezed by changing gravitational forces. That squeezing warms its interior. If several moons interact, they can maintain those elliptical orbits through resonances, as Jupiter's moons do. A moon of a rogue planet could therefore be an ocean world even if the planet itself is not. In some ways, moons might be the most promising places in rogue systems, because tidal heating can be strong and long-lasting. A starless giant planet could carry a small family of moons through the galaxy, and one of those moons might keep an ocean under ice, warmed by gravity instead of sunlight. That image is wonderfully odd. Not a planet in a habitable zone, but a moon in a gravity zone warmed by orbital flexing in the dark. Could such an ocean be habitable? The honest answer is perhaps under specific conditions, but we should tread gently. Habitability is not the same as inhabited. A place can have liquid water and still have no life. It can have energy, but not the right chemistry. It can have chemistry, but not enough stability. It can be stable, but sealed off from important ingredients. Life, as far as we know, requires liquid water, energy, useful chemical elements, and time. A rogue planet's hidden ocean might provide some of these. Water, yes. Energy from hydrothermal vents or chemical reactions, maybe. Elements from rock, if the ocean touches rock, possibly. Long time scales, perhaps, if the heat balance holds. But whether life begins there is a much deeper question. We only know one world where life definitely began, and you are sitting on it, or lying on it, or perhaps listening to this while wrapped in a blanket on it. If life did exist in a rogue planet's hidden ocean, it would almost certainly not be the kind of life that writes postcards about the view. There would be no photosynthesis in the ordinary sense, because there is no sunlight. Any life would likely be microbial, living near chemical energy sources, perhaps around hydrothermal vents or within porous rock. It might resemble Earth's deep biosphere more than its surface biosphere. On Earth, microbes live deep underground, in ocean crust, in sediments, and around vents, using chemical pathways that do not require sunlight directly. A rogue ocean biosphere, if it existed, might be slow, sparse, and efficient. Energy would be limited. Growth could be sluggish. Ecosystems might be small and localized. The dark ocean would not be a colorful coral reef. It might be a quiet microbial world, surviving on the planet's faint internal warmth. There is something calming about that, in a very strange way. We often imagine life as something that needs brightness, abundance, and surface activity. A rogue planet asks us to imagine life as patience, not forests spreading under a sun, but chemistry continuing in a sealed ocean, not seasons but slow circulation. Not daylight, but heat rising through rock. Not birdsong, but microbial metabolism near a vent. It is a much quieter version of habitability. If Earth is a house with windows open to the sun, a rogue ocean world is a cellar with a small furnace still burning. Not grand, not obvious, but perhaps enough. How would we ever know whether such an ocean exists? That is the difficult part. For rogue planets far away, detecting a subsurface ocean directly would be extremely hard. If the planet is found by microlensing, we may only know its mass and that it exists, not its surface or interior. If it is a young, directly imaged object, it is likely a gas giant or planetary mass object, not a cold, rocky ocean world we can inspect. If a rogue planet passed very near the solar system, within hundreds or thousands of astronomical units. Perhaps future far-infrared telescopes could detect its thermal emission. Its temperature might reveal whether it has more heat trapped than expected. But seeing through ice into an ocean would be another challenge entirely. For moons in our own solar system, spacecraft can measure magnetic fields, gravity, surface features, plumes, and ice properties. For rogue planets between stars, we are usually far more limited. The hidden ocean may be hidden not only beneath ice, but beneath distance. Still, science often begins with what can be inferred. If future surveys find many Earth-mass rogue planets, models can estimate how many might retain water, heat, and ice shells. If some pass close enough, their infrared glow might reveal temperature. If a rogue planet has a moon, and the system can be detected, orbital dynamics might hint at tidal heating. If a young rogue object has a disk, that tells us about formation. If a cold rogue planet lenses a background star, that gives us mass, and maybe hints about whether it is isolated. Each clue is small. Together they build a map of possibilities. We may not soon drill into a rogue planet's ice, which is probably for the best since the travel time alone would be very bad for snacks, but we can still understand the physics well enough to ask which worlds could keep oceans and which could not. The ice shell itself would be a world of its own. At the surface it might be brittle, cracked, and extremely cold. Deeper down, ice becomes warmer and may deform slowly, flowing over long timescales like rock does in a planet's mantle. There may be layers of different ice forms. There may be pockets of brine, trapped salts, or fractures where warmer material rises. If the ocean below is active, it might push against the shell, creating ridges or cracks, though without sunlight. These features would be seen only by instruments or perhaps by the faint light of stars. If pressure builds, liquid might occasionally erupt upward and freeze, creating cryovolcanic features. On an isolated rogue planet, such activity would depend entirely on internal energy. The surface might be mostly still, but still is not the same as dead. Geological time is patient enough to make even ice move. If the ocean touches a rocky seafloor, the bottom may be the most important place. There, water and rock can react. Serpentinization, for example, is a process in which certain rocks react with water to produce hydrogen. On Earth, hydrogen can be used by microbes as an energy source. Hydrothermal circulation can bring oxidants and reductants together, creating chemical disequilibrium, which is a technical way of saying nature has not finished balancing the books. Life loves unbalanced books, at least chemically. It can use the difference to power metabolism. A rogue planet's ocean would need such gradients to remain useful for life. A perfectly mixed, chemically exhausted ocean might be liquid but not lively. A vent system, on the other hand, can keep refreshing the chemistry, providing localized zones where energy flows. One possible problem is isolation from the surface. On Earth, the surface and deep ocean exchange material. Oxygen produced by photosynthesis eventually affects ocean chemistry. Weathering delivers nutrients from continents. A rogue planet's sealed ocean may not get that surface input, especially if the ice is thick and stagnant. That could limit available energy or nutrients, but if the ocean interacts with rock, it still has an internal source of chemistry. Some icy moons may have similar issues, and scientists study whether cracks, convection, plumes, or ice recycling can move materials between surface and ocean. On a rogue planet, surface radiation chemistry would be weaker without a nearby star, though cosmic rays may still affect upper layers. The question becomes whether enough ingredients can circulate without sunlight. The answer probably varies from world to world, which is a scientifically polite way of saying the universe has not made this easy. The idea of a rogue planet ocean also changes how we think about the habitable zone. Usually the habitable zone is a ring around a star where a planet with the right atmosphere might maintain liquid water on its surface. Move too close and water boils away. Move too far and it freezes. This is a useful idea but not the whole story. A subsurface ocean does not need to be in the classic habitable zone. Europa is outside the Sun's traditional habitable zone, yet it likely has an ocean. Enceladus is farther still, and it has a hidden sea. A rogue planet is beyond all stellar habitable zones, but if it has enough internal heat and insulation, it may create its own private habitable layer. Not a habitable zone around a star, but a habitable pocket inside a planet. A small warm room in a very large dark house. It is worth pausing on how strange that is. A planet could be invisible to most telescopes, frozen at the surface, separated from every star, and still hold liquid water below. It could travel between stellar systems for billions of years, while an ocean quietly circulates under ice. It might pass through regions of the galaxy where bright stars are being born, then into darker stretches where the night sky thins out. None of that would matter much to the ocean below. Its clock would be internal. Its seasons would be heat flow, chemistry, and pressure. Its sky would be the underside of the ice. If anything lived there, the galaxy's stars would be irrelevant, except as the ancient factories that made the atoms in the first place. And if there is no life, the ocean is still remarkable. A lifeless ocean beneath ice on a rogue planet would still be a preserved environment, a deep chemical laboratory sealed away from starlight. It might hold records of the planet's formation, its ejection, its cooling, and its internal evolution. Its salinity, isotopes, dissolved minerals, and ice structure would be clues to a history we can barely imagine. The ocean would not need life to be scientifically precious. It would already be proof that planets can keep complexity in the dark. So could a rogue planet keep an ocean beneath its ice? Yes, under the right conditions. It would need water, insulation, and enough internal or tidal heat. It would likely need sufficient mass to hold heat for long periods, or a thick ice shell, or a frozen atmosphere, or a dense hydrogen blanket, or moons that help create tidal warmth. It would need the balance to last, not just for a brief moment, but long enough for the ocean to matter. Some rogue worlds may fail this test and freeze solid. Some may never have water. Some may be gas giants with no solid surface but ocean-bearing moons. Some may be large, icy rocky wanderers with deep hidden seas. The category is wide enough for many outcomes. And that is what makes rogue planets so quietly powerful in the imagination. They remove the sun and ask what remains. They strip away daylight and reveal the importance of inner heat. They take the familiar idea of an ocean and hide it under a roof of ice, in a place where no morning ever comes. They remind us that habitability is not always bright, warm, and visible. Sometimes, if it exists at all, it may be buried, pressurized, dark, and slow. A private sea moving beneath a frozen shell, carried through interstellar space by a planet with no sunrise, no sunset, and no star to call its own. If a rogue planet could keep a secret sea inside, what would it feel like to stand outside on such a world, under a starless kind of night, with the ice beneath your feet and the whole galaxy spread overhead? Standing on a starless world would begin with one simple fact that your body would understand long before your mind finished explaining it. There would be no daylight coming, not soon. Not later. Not after the clouds clear. Not when the planet turns a little farther. If you stood on the surface of a rogue planet, assuming it had a surface you could stand on, and assuming you were wearing the kind of protective suit that makes ordinary winter clothing look like a napkin with sleeves, the sky above you would remain dark. It might be filled with stars, perhaps more stars than you have ever seen from Earth, sharp and steady if the air is thin, blurred or hidden if the atmosphere is thick. But no single star would dominate the sky. No sun would rise over the horizon. No warm disk would climb upward and turn black ground into morning. The whole idea of morning would become uncertain, like a word from a language the planet never learned. At first, the darkness might feel like night, because night is the closest thing we know. But it would not really be Earth night. Earth night still belongs to the sun, The ground beneath you was warmed by sunlight hours earlier. The air still holds heat from the day. The moon, if it is present, is reflecting sunlight. Even the rhythm in your body, the sense that night is temporary and morning will come, is built around a star. On a rogue planet, darkness is not one half of a daily cycle. It is the background condition. The sky may rotate overhead if the planet spins, and the stars may rise and set, but the surface would not brighten in the familiar way. You could watch constellations move for hours and still never see dawn. It would be like standing inside a clock whose hands turn, but whose lamp has been removed. The surface itself would depend on the kind of rogue planet. If it were a rocky world, perhaps something roughly Earth-sized or larger, the ground might be covered in ice, frozen gases, dark rock, or a mixture of all three. If it once had oceans, the top may now be sealed under a thick crust of ice. If it had an atmosphere, some gases may have condensed onto the surface as frost or snow, depending on temperature and pressure. Carbon dioxide could form dry ice deposits. Nitrogen might freeze in colder conditions. Methane, carbon monoxide, and other compounds could take part in their own strange weather, if the temperatures are right. This is not weather as we know it, with sunshine driving evaporation and clouds carrying rain over hills. It is chemistry responding to cold. Gases decide whether to stay in the air or lie down on the ground as frost, which is a very planetary way of saying, "I have had enough of being a gas, thank you." If the rogue planet had almost no atmosphere, standing there would feel visually crisp and physically impossible without protection. There would be no wind to hear, no air to carry sound, no blue scattering in the sky, and no softening of the stars. The horizon might curve under a black dome, with the Milky Way spread overhead like a pale band of unresolved suns. Your own footsteps would not make sound outside your suit, because sound needs air or some other medium to travel. You might feel vibrations through your boots if you walked, but the landscape itself would be silent. A falling rock would strike the ground without an audible crack in the open vacuum. It is hard for a human mind to imagine a place where movement does not automatically make sound, because on Earth even quiet places are full of tiny noises. Wind in grass, distant traffic, wood settling in a house, blood moving in your ears. On a bare rogue planet, the universe outside your suit would offer none of that. If the planet had a thick atmosphere, the experience would be different, though not necessarily friendlier. A dense atmosphere could hide the stars behind clouds or haze. It could create winds, pressure, and perhaps storms driven by internal heat. The sky might be black, brown, grey, or dimly glowing in infrared beyond human sight. Lightning might flicker inside cloud decks, if the atmosphere is active enough. If the atmosphere were rich in hydrogen and very thick, it might trap internal heat, making the lower atmosphere warmer than a bare surface would be. But high pressure could make the environment deadly. A human visitor might not stand under an open star field at all, but under a deep, dark, gaseous ceiling, crushed by pressure and surrounded by strange chemical weather. A rogue planet with a warm surface would not automatically be comfortable. Warmth is only one requirement for comfort, and the universe has a habit of meeting one requirement while ignoring the rest entirely. Gravity would be another immediate difference. A rogue planet could be smaller than Earth, larger than Earth, or as massive as several Jupiters if we are speaking broadly about planetary mass wanderers. On a rocky world smaller than Earth, your steps might be light, slow, and almost bouncing. On a super-Earth, each step could feel heavy, your suit pulling down with extra force, your muscles working harder. On a gas giant, there may be no solid surface in the usual sense, so standing becomes a problem before the sightseeing even begins. You might descend through clouds into greater and greater pressure until the atmosphere becomes a dense fluid and your spacecraft has a very serious conversation with physics. So when we imagine standing on a starless world, we're usually imagining a rocky or icy rogue planet, or perhaps a large moon travelling with a rogue giant. That is where boots, ice, horizons, and hidden oceans make the most sense. The temperature at the surface could be brutally low. On a bare rogue Earth, the surface would likely become far colder than any natural place humans experience today. Water ice would be hard as rock. The air, if much remained, could be thin and frigid. The ground might radiate away heat until only the planet's faint internal warmth seeped upward from below. You would not feel cold in the ordinary way if your suit worked, just as an astronaut does not feel the vacuum of space directly, but the environment would be constantly trying to steal heat from anything warm. Machinery would need power, batteries would suffer, lubricants could freeze, materials could become brittle. Every breath, every instrument, every joint in a suit would depend on energy brought from elsewhere. On Earth, survival is supported by a whole planet-wide background of sunlight-driven systems. On a rogue planet's surface, survival would be an engineering project against the dark. And then there is the psychological part. Humans are not only bodies. We are creatures of cues. We use light to tell time. We use sunrise to wake, sunset to settle, seasonal change to mark the year. On a starless world, those cues vanish. A day might still exist as one rotation of the planet, but nothing outside would announce it unless you track the stars. Your circadian rhythm would need artificial light. Your sense of direction might depend on instruments because there would be no sun to orient you. If the landscape were flat ice under a repeating star field, it might become disorienting very quickly. Even the idea of distance would change in low light. Without sunlight and shadows, features can become difficult to judge. Your lamp would create the only familiar pool of visibility, and beyond it, the land would disappear into darkness. You would carry your own little sunrise with you, powered by a battery. Could life survive there? On the surface, for most rogue planets, the answer is probably not in the familiar Earth surface sense. Photosynthetic life would have no steady sunlight to use. Plants, algae, and the complex food webs that depend on them would fail unless there were another energy source. Surface temperatures might be too low. Radiation from cosmic rays could be a problem if there is no protective atmosphere or magnetic field, though a thick atmosphere or ice layer could provide shielding. Liquid water on the surface would be unlikely for a cold, bare world. Even if the planet had a dense insulating atmosphere that allowed liquid water, the pressure, chemistry, and darkness might make the surface very unlike Earth. So if we are picturing forests under starlight, animals wandering icy plains, or little glowing flowers waving in the wind, we should gently set that image aside. It is charming, but not the most likely science. The better place to look is below. Life, if it survived or began on such a world, would most likely hide beneath the surface, where conditions are buffered from the cold of space. An ice shell can protect an ocean. Rock can hold heat. Water can circulate through minerals. Chemical reactions can release energy. This is not just imagination borrowed from science fiction. On Earth, deep-sea hydrothermal vents support ecosystems in complete darkness. Sunlight does not reach those depths in any useful way. Instead, microbes use chemical energy from vent fluids, and larger organisms depend on those microbes. The whole system teaches us that life does not always need sunlight directly. It needs energy, liquid water, usable chemistry, and enough stability for biology to do its slow, complicated work. A rogue planet with an ocean beneath ice could provide some of those ingredients. The water would be hidden below a frozen shell. The energy might come from geothermal heat, radioactive decay in the rocky interior, or tidal heating if the planet has moons or a companion. The chemistry could come from water interacting with rock at the seafloor. If hydrothermal vents existed, they might release hydrogen, methane, sulfides, metals, and other compounds into the ocean. Microbes, if present, might use chemical gradients as energy sources. They would not know or care that no star was shining above the ice. Their world would be the vent, the water, the minerals, and the thin boundary where useful reactions happen. For them, the sky would be irrelevant. The underside of the ice might be as unreachable and unimportant as the stars are to a worm in deep soil, but surviving and starting are not the same thing. This is an important distinction. If a planet once had life before being ejected from its star system, some deep subsurface life might survive the loss of sunlight, especially if it was already independent of sunlight. Microbes underground or near hydrothermal systems would be better candidates than surface organisms. But if the rogue planet never had life, could life begin there in the first place? That is harder. The origin of life on Earth is still an open scientific question. Hydrothermal vents are one possible environment where prebiotic chemistry could have happened because they provide energy, minerals, and gradients. But we do not know exactly what combination of conditions is required. A rogue planet's hidden ocean might have some of those conditions, but whether it could actually produce life is uncertain. The honest answer is that such a world might be habitable in a limited sense, but we cannot say it would be inhabited. The word habitable can be a little slippery. In everyday language, it sounds like a place where someone could move in, unpack a bag, and complain about the heating. In astrobiology, it usually means an environment that could support life as we know it, at least microbial life, under certain conditions. A deep ocean under ice might be habitable even if no human could visit without a very expensive submarine, a drilling system, and a heroic disregard for travel distance. A vent system in total darkness might be habitable for microbes but not for trees, fish, or anything with ambitions involving sunlight. So when we ask whether life could survive on a rogue planet, we need to ask what kind of life, where on the planet, for how long, and with what energy source. The answer changes depending on the details. A surface organism like a plant would not do well. A microbe living deep in rock might. An animal-like organism would require a richer ecosystem and more available energy, which may be much less likely. A biosphere supported only by chemical energy could be sparse and slow. On Earth, sunlight powers a huge surface biosphere because it delivers abundant energy. Hydrothermal vent ecosystems are impressive, but they are localized and limited by the chemistry available. A rogue planet's hidden ocean, if it has life, may be more like that. Small pockets of activity near vents, microbial mats, slow metabolisms, long periods of little change, perhaps life that measures time not in days or seasons, but in the movement of fluids through rock and the gradual cooling of a planet's interior. There is also the question of nutrients. Life needs more than water and heat. It needs elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, and various metals. Some of these could be present in the ocean or supplied by rock-water reactions. But if the ocean is sealed away beneath ice and does not exchange much material with the surface or rocky interior, nutrients could become limited. If high-pressure ice separates the ocean from the rocky mantle, the chemistry might be less favourable. If the seafloor is active, the situation improves. If the ice shell convects or cracks, materials may cycle. If there are oxidants created near the surface and somehow transported downward, that could add more chemical energy. These details are why astrobiology is careful. Liquid water is exciting, but water alone is not a guarantee. A sterile swimming pool is liquid water too, and nobody expects it to invent a biosphere between cleanings. A rogue planet with a thick atmosphere and surface liquid water is another possibility, though it may be rarer. If a dense hydrogen atmosphere traps enough internal heat, the surface could remain warm. Such a planet might have lakes or oceans under a dark, high-pressure sky. Life there would still face the absence of sunlight, but chemical energy could exist at the seafloor or in the atmosphere. Lightning, volcanic activity, and chemical disequilibrium might provide some pathways for prebiotic chemistry. But again, pressure and composition matter. A thick hydrogen atmosphere could make the surface environment very different from Earth's. It might be warm, but chemically strange. It might have no oxygen. It might be difficult for complex life as we know it. Microbes are the more reasonable starting point. Moons of rogue planets may be especially interesting. If a rogue gas giant carries moons, Tidal heating could keep a moon's interior warm. A moon like Europa or Enceladus, but no longer orbiting a star, might still maintain a subsurface ocean if tidal flexing continues. The rogue giant's gravity would squeeze and stretch the moon as it orbits. Other moons could help maintain orbital resonances, keeping the flexing going over long periods. In such a case, the moon may be more habitable than the planet. It would still be dark at the surface, but below the ice, the ocean could be warmed by gravity. Around a normal star, we often look for planets in habitable zones. Around a rogue giant, we might think instead about moons in tidal heating zones, where orbital energy replaces sunlight as the main source of warmth. It is a different kind of habitability, dimmer, stranger, and far less familiar, but not meaningless. If you stood on such a moon, the view might be even more extraordinary than standing on the rogue planet itself. The giant planet would hang in the sky, not shining brightly like a moonlit object around a star, but looming as a dark disk against the stars, perhaps faintly glowing in infrared if your eyes could see that way. If it had rings, they might appear as a thin black arc cutting across the starfield. The ground beneath you might be cracked ice. Tidal stresses could open fractures. Plumes might spray water vapour or ice grains into space if the moon is active, freezing into glittering particles in your lights. The surface would be deadly cold and dark, but below it the ocean might be moving. The real action would not be where you stood. It would be hidden under your feet. On the surface of a rogue planet, one of the most beautiful things might be the stars, if the atmosphere allows them to be seen. Without a nearby sun, the sky would not be washed out. The Milky Way might be visible in great detail. The galactic centre, if in view and not blocked by dust, might glow as a dense region of stars. Nearby stars would change slowly over centuries and millennia as the planet moves. If the rogue world passed through a star-forming region, the sky might become richer for a time. If it drifted into a more isolated region, the stars might thin. There would be no constellations in the human cultural sense, unless someone living there invented them, and even then the constellations would depend on where in the galaxy the planet happened to be. The sky would be a map not of a home system, but of the galaxy itself. For any life under the ice, that sky would not matter. That contrast is almost funny in a quiet way. A human visitor would be overwhelmed by the starfield, by the silence, by the absence of sunrise, but a microbe near a hydrothermal vent would be concerned with hydrogen, minerals, temperature, acidity, and membranes. It would not care whether the Milky Way looked magnificent overhead. It would not know there was an overhead. This is one of the useful humilities of astrobiology. We often imagine life from the point of view of creatures with eyes, but life does not begin with a view. It begins with chemistry that can persist, copy, and evolve. If rogue planets can host life at all, it may be life without scenery. Could humans survive there? Only with technology, and a great deal of it. A base on a starless world would need power independent of sunlight, likely nuclear or geothermal if available. It would need sealed habitats, artificial light, heat, air recycling, water extraction, radiation shielding, and reliable machinery in extreme cold. Solar panels would be useless except perhaps for faint starlight, which is not a serious power source. Agriculture would need artificial lighting or chemical energy systems. Timekeeping would be artificial. Navigation would depend on stars, instruments, and perhaps orbiters. It would be one of the least forgiving environments imaginable, not because it is violent, but because it gives so little. A hurricane is dramatic. A rogue planet is simply indifferent. It does not blow you away. It lets the heat leak out of everything you brought. Even so, humans have always been drawn to extreme places, at least in imagination. We send probes to icy moons, landers to Mars, orbiters to distant planets, and telescopes into space. A rogue planet would be far harder to reach than any planet in our solar system. Unless one passed unusually close by, which would be rare and potentially gravitationally interesting in ways we might not appreciate. But as a thought experiment, standing there teaches us what our own world gives us every day. The sun is not just brightness. The atmosphere is not just air. The ground is not just something solid beneath our feet. Earth is a web of energy flows, protections, cycles, and balances. Remove the star, and the surface world collapses into cold. Keep only the interior, and habitability retreats downward into hidden places. That retreat is important. It tells us that life, if it exists beyond Earth, may not always announce itself from the surface. We often search for gases in atmospheres, colours on planets, patterns in reflected light. But a rogue planet with life under ice might have almost no visible sign from afar. Its biosphere, if present, could be sealed away, producing little that escapes into space. It might be one of the hardest living worlds to detect. A planet could carry life through the galaxy and still appear, from a distance, like a cold, dark mass. That's both exciting and frustrating. Exciting because it expands the possible homes for life. Frustrating because homes hidden under kilometers of ice do not make astronomy easy. The universe, once again, has not optimized itself for our convenience. If life survived on a rogue planet after ejection, it might also preserve a strange record of loss. Imagine a world that once had a star, once had oceans under daylight, perhaps even simple life in surface waters. Then gravitational chaos throws it outward. The surface freezes. Photosynthetic life dies. The atmosphere changes. But microbes deep below continue, protected by rock and water, living off chemical energy. Over millions of years, the old surface biosphere becomes a fossil memory. The deep biosphere becomes the main biosphere. The planet no longer has seasons, but life persists in the dark, reduced, hidden, patient. That is not a cheerful story exactly, but it is not total extinction either. It is survival by moving inward. For a world born without a star, life would have no surface paths to lose. If it arose at all, it would begin in darkness. That is stranger still. There would be no first sunrise for life, no early shallow seas warmed by a young star, no day-night cycle shaping chemistry. Instead, life would have to begin around internal energy sources, perhaps vents, pores in rock, mineral surfaces, and chemical gradients in a hidden ocean. Some origin of life ideas on Earth already involve hydrothermal environments, so the possibility is not absurd. But whether such conditions are enough without surface processes is unknown. The absence of ultraviolet light from a star might remove some chemical pathways, while protecting fragile molecules from destruction. The darkness could be both obstacle and shelter. As usual, the answer is not simple, which is rather inconsiderate of the cosmos, but good for long, sleepy explanations. Complex life would be much harder. Complexity usually requires abundant energy over long periods. On Earth, oxygen from photosynthesis helped make large active animals possible. A rogue ocean biosphere might not produce large amounts of oxygen unless it has some alternative chemistry or oxidants transported from the ice. Without strong energy flow, life may remain microbial. That does not make it unimportant. Microbes are not simple in any dismissive sense. They shaped Earth for billions of years before animals appeared. They invented metabolic pathways that still run the planet's chemistry. A microbial biosphere under rogue ice would be one of the most profound discoveries imaginable. It would tell us that life can survive, or even begin, without a star. Not life like us, perhaps, but life nonetheless. So what would it be like to stand on a starless world? It would be dark, cold, silent, and deeply unfamiliar. The stars might be breathtaking, or hidden behind dense clouds. The ground might be frozen air, cracked ice, hard rock, or pressure-shaped snow of strange compounds. There would be no natural day, no warm weather, no sunlight on your face. Every moment outside would depend on artificial heat and light. You would be standing on the outside of a world whose most interesting places might be unreachable below. The surface would seem dead. The planet's real life, if it had any, would likely be beneath you, under ice, near rock, in water warmed by the slow leakage of internal energy. And that may be the best way to understand the survival question. On a rogue planet, life would not spread outward into sunlight. It would shelter inward toward heat. It would not follow the day, it would follow chemistry. It would not build forests under a blue sky. It might build microbial communities around vents in black water, sealed beneath an ice roof thicker than mountains are tall. It would be life reduced to essentials: liquid water, energy, chemistry, and time. Whether such life exists anywhere is unknown. But the possibility is enough to change how we think about planets. A world does not need to shine to be interesting. It does not need a sunrise to have layers. It does not need a star to keep a secret. The number may be the strangest part of all, because once you accept that rogue planets can exist, the next question arrives quietly and then refuses to leave. How many are out there? Not one or two odd worlds drifting through the dark like rare mistakes, but how many in total, across the whole Milky Way hidden between the stars? Are they unusual, like cosmic lost coins found only now and then? Or are they everywhere, an enormous invisible population moving through the galaxy without sunlight, without names, and without any easy way for us to notice them? The honest answer is that we do not know yet with certainty, and that uncertainty is part of the wonder. We are standing at the beginning of a census of worlds that do not shine, do not orbit stars, and often announce themselves only for a few hours when their gravity bends the light of something behind them. For a long time, planets were almost always imagined as members of solar systems. A star was the centre. Planets were the companions. Moons were companions of companions. Asteroids, comets, dust, and ice filled in the smaller parts of the picture. It was a family arrangement, and because our own solar system is the example closest to us, it shaped our intuition deeply. But the galaxy is not required to behave like the neighbourhood we grew up in. Over the past few decades, exoplanet discoveries have already shown us that planetary systems can be much stranger than our own. Giant planets can orbit extremely close to their stars. Rocky worlds can whip around dim red dwarfs in only a few days. Planets can orbit 2 stars. Some worlds are puffier than expected, darker than expected, hotter than expected, or packed into systems that look like someone arranged marbles on a very small tabletop and then trusted gravity to sort out the details. Rogue planets take the next step. They say that some worlds may not be in systems at all, at least not in the local sense. Counting them is difficult, because our usual planet-finding methods often depend on stars. If a planet crosses in front of its star, we can see a tiny dip in starlight. If a planet tugs on its star, we can measure a wobble. If a planet is wide and young and bright enough, we might image it near its star. But a rogue planet does not offer a parent star as a clue. It is not making a regular transit. It is not pulling on a visible sun. It is not part of a neat repeating pattern. A rogue planet can drift for millions or billions of years through interstellar space without doing anything obvious from our point of view. It is there, but being there is not enough. Astronomy needs signals, and a cold, dark world is rather stingy with signals. This is why the estimates have changed over time and why they may keep changing. Early microlensing studies suggested that Jupiter-mass rogue planets might be extremely common, perhaps even more common than stars. Later work questioned whether the abundance of Jupiter-mass free floaters was that high, suggesting that smaller free-floating worlds may dominate instead. Direct imaging surveys in young regions have found many giant candidates, but those surveys mostly see young, warm, fairly massive objects. Microlensing can detect smaller, colder objects, but it catches them only during brief alignments with background stars. Each method sees only part of the population. It is a little like trying to count all the animals in a forest by listening for owls, looking for footprints in mud, and occasionally noticing a fish jump in a pond. Each clue is real, but none of them alone tells you the whole forest. The Milky Way contains somewhere on the order of hundreds of billions of stars. That number alone is enough to make the mind stretch uncomfortably, like trying to fold a blanket that is also a continent. If rogue planets are only a small fraction as common as stars, there could still be billions of them. If they are as common as stars, or more common, the number becomes hundreds of billions or even trillions. NASA has reported research suggesting that rogue planets may greatly outnumber planets bound to stars, with estimates reaching into the trillions of worlds wandering alone. Other studies and surveys point especially to many low-mass rogue planets, perhaps Earth mass, Mars mass, or even smaller. The exact numbers remain uncertain, but the direction of the evidence is clear enough to be astonishing. Rogue planets are not just theoretical curiosities, they may be a major part of the galaxy's inventory. Think about that gently for a moment. We look up at the night sky and see stars, bright ones, faint ones, constellations, the hazy band of the Milky Way if the sky is dark enough. The stars are what reveal the galaxy to human eyes. They are the lamps. They are the visible architecture. But between them there may be an enormous hidden population of planets, unseen by ordinary vision. A dark galaxy inside the bright one. Not dark matter, not mysterious in that sense, but ordinary planetary material, rock, ice, gas, atmospheres, moons perhaps, all moving without a nearby sun. The visible galaxy may be only the glittering surface of a much larger population of worlds. The most conservative way to speak is by mass and detection method. Giant rogue planets, those with masses comparable to Jupiter, can sometimes be seen directly when they are young. In star-forming regions, where objects are only a few million years old, they still glow with leftover heat from formation. ESO's survey in the Scorpius and Ophiuchus region found at least 70 new rogue planet candidates with masses comparable to Jupiter. That was the largest group discovered at the time, and it suggested that many more such giant free floaters may be present across the Milky Way. But giant planets are only one part of the story. They are easier to see when young, so they can bias our imagination. Smaller rogue planets could be vastly more numerous and far harder to detect. A cold Earth mass rogue planet does not glow in a way we can easily see across interstellar distances. It may be found only if it lenses a background star, and even then the event may be very brief. Microlensing is therefore essential for the true census. When a rogue planet passes in front of a distant star, its gravity bends the star's light and briefly makes it brighter. The shorter the event, generally speaking, the smaller the lensing object may be, although distance and motion also matter. Very low-mass rogue planets can create micro-lensing events lasting only hours or less. That makes them difficult to catch, but not impossible. Projects like OGLE, MOA, KMT-NET, and future space missions are designed to monitor huge numbers of stars repeatedly, waiting for these little flashes of gravitational evidence. The planet itself remains dark, the background star brightens, and the light curve becomes a tiny confession from gravity. A major difficulty is that microlensing events can be ambiguous. If a planet is on a very wide orbit around a star far enough that the star's effect does not appear clearly in the lensing signal, it can look similar to a truly unbound planet. So some candidates are described carefully as free-floating or wide-orbit planets. That may sound like a small distinction, but it matters for the population count. If many candidates are actually bound to distant stars, then the number of truly unbound rogue planets would be smaller. If most are genuinely unbound, then the galaxy is even more filled with wandering worlds. Astronomers often search for signs of a host star in the microlensing data, or later imaging, but the absence of evidence is not always simple. A faint host could be too far away, too dim, or hidden in the crowded background. Again, the universe does not always label its objects in large friendly print. The 2026 microlensing measurement of KMT-2 024-BLG-O 792/OGLE-2 024-BLG-O516 is important because it helped break one of the usual uncertainties. By observing the event from both ground-based telescopes and the Gaia spacecraft, astronomers could use the difference in viewpoint to measure the lens more directly. The object turned out to have a mass around a fifth of Jupiter's mass, roughly Saturn-like, and no evidence was found for a host star within a wide range. It may be truly free-floating, or at least very widely separated from any star. This kind of direct mass measurement is a breakthrough because it gives firmer ground beneath the population question. Instead of only saying, something planet-like probably passed in front of a star, astronomers could say much more about its mass and distance. One wayed wanderer does not count the whole galaxy, but it proves the scale is real. Future missions are expected to change the story dramatically. NASA's Nancy Grace Roman Space Telescope is especially important because it will observe from space with a wide field of view and sharp infrared vision. It is designed to watch dense star fields and catch micro-lensing events with the steadiness and sensitivity needed to find many low-mass rogue planets. Estimates suggest Roman could find hundreds of Earth-mass rogue worlds if current population models are right. That is not just a larger catalogue, it is a different kind of knowledge. Once astronomers have hundreds of detections, they can begin to measure the mass distribution. Are small rogue planets far more common than giant ones? Does the number rise steeply toward Mars-mass objects? Is there a cut-off? Do the numbers match what we expect from planet-planet scattering, or from star-like formation, or from both? A population is like a fingerprint of origin. The number also depends on where rogue planets come from. If most are ejected from young planetary systems, then their abundance tells us how chaotic planet formation is. A system like ours may look calm now, but perhaps many systems throw away several worlds before settling down. The more crowded a young system is, the more giant planets migrate, the more close encounters occur, the more ejections may happen. Small planets could be especially easy to scatter. Outer icy worlds may be easier to loosen. If every forming system loses one or two planets, the galaxy quickly fills with wanderers. If some lose dozens of smaller bodies, the numbers rise even more. The rogue planet population then becomes a record of old gravitational arguments, a dark archive of planets that did not remain at home. If many form alone, like tiny cloud collapse objects, then the count tells a different story. It would mean that star formation itself extends down into planetary masses more often than expected. A molecular cloud can fragment into stars, brown dwarfs, and perhaps planetary mass bodies that never orbit a star. In that case, the number of giant rogue planets in young regions could reflect the low-mass end of star formation. The galaxy would not only eject worlds, it would manufacture solitary planet-like objects directly. And if both pathways operate, as seems likely, then the population is mixed. Some are exiles, some are born alone, some are forming embryos cut off early, some are wide-orbit planets that only appear isolated from far away. The count is not just how many, it is how many of each kind. There is also the question of size. Giant rogue planets are easier to talk about because we have found more examples directly, but smaller ones may dominate the numbers. Think of planets in normal systems. Small planets are common. The galaxy seems very good at making worlds between Earth and Neptune in size, even though our solar system lacks that exact type. If young systems frequently eject small planets or planetary embryos, the Milky Way could contain huge numbers of rocky or icy free floaters. These are the objects most relevant to hidden oceans, frozen surfaces, and possible subsurface habitability. They are also the hardest to find. A Jupiter-mass rogue planet may glow when young. An Earth-mass rogue planet older than 1 billion years may be almost invisible except through micro-lensing. A Mars-mass rogue planet may create an even shorter lensing event. Counting these is like counting dark seeds scattered across a field at night, while only seeing them when lightning flashes. The answer then may not be one number. It may be a range, and a wide one. Several billion free-floating giant planets may roam the Milky Way. There may be hundreds of billions or trillions of lower-mass rogue planets, if the most ambitious estimates hold. There may be more rogue planets than stars, perhaps far more, especially at smaller masses. But because the methods are still developing, those numbers should be held with care, not thrown around like confetti. The important thing is not that we know the exact total today. The important thing is that the total may be enormous, and that future surveys are close to turning a rough guess into a measured population. Imagine the galaxy as a city at night. The stars are the lit windows. You can see them from far away. You can map the neighbourhoods by their glow. But between the windows are roads, alleys, parks, courtyards, hidden rooms, and people walking in the dark. Rogue planets are like those unlit travellers. They do not define the skyline, but they may be everywhere within it. We have only recently learned how to notice them. A tiny infrared glow here, a brief micro-lensing flash there, a young object moving with a stellar association, a direct mass measurement from a lucky alignment. Each discovery is like hearing a footstep in the dark and realizing the city is far busier than the lights alone suggested. The Milky Way may therefore be less like a collection of star-centered systems and more like a vast gravitational ecosystem. Stars dominate the light. Gas clouds feed new stars. Dark matter shapes the whole structure. Black holes, neutron stars, white dwarfs, brown dwarfs, planets, moons, asteroids, comets, and dust all move through the same enormous field. Rogue planets belong to this ecosystem. They are not mistakes outside the map. They are part of the map we could not see before. Some may cross spiral arms. Some may drift through old stellar populations near the galactic bulge. Some may remain in loose young associations. Some may pass near stars without being captured. Some may spend billions of years almost unchanged, their surfaces frozen and their interiors slowly cooling. Their number is a measure of how much hidden structure the galaxy contains. One day, perhaps, we will have a proper rogue planet census. Not a perfect one, because astronomy rarely grants perfection, but a much better one than we have now. We may know how many Jupiter mass wanderers exist, how many Neptune mass, how many Earth mass, how many Mars mass. We may know whether they are common in the galactic bulge or disk, whether they trace star formation, whether they cluster by age or composition. We may even identify nearby examples close enough for future telescopes to study directly. A nearby cold rogue planet would be an extraordinary target. Its infrared glow, atmosphere, moons if any, and temperature could tell us what a starless world becomes after long ages in the dark. Until then, the safest answer is also the most intriguing. There are probably many, maybe billions of giant ones, possibly far more smaller ones. Perhaps enough that the spaces between stars are not empty in the way we once imagined. They may be filled with worlds we cannot see, worlds that carry ice, gas, rock, hidden heat, and sometimes moons through the long dark lanes of the Milky Way. And if that is true, then the night between stars is not merely a gap. It is a place with its own population, its own histories, its own quiet travellers. The galaxy is bright with stars, yes, but it may also be crowded with unseen planets, moving without sunrise, without sunset, and without anyone nearby to call them home. By the time we reach this point in the journey, a rogue planet no longer feels like a simple object. At the beginning, it may have sounded like a lonely world with no sun, an astronomical oddity drifting through the dark because something went wrong. But now, after following the idea through formation, ejection, hidden heat, possible oceans, difficult searches, and uncertain numbers, it becomes something richer. A rogue planet is not just a planet without a star. It is a question moving through space, What is a world without daylight? What remains when the centre is gone? How much of a planet's story belongs to its sun, and how much belongs to the planet itself? These are not only scientific questions, although they are scientific. They're also human questions, because we cannot help bringing our own sense of home, separation, darkness, and survival into the way we imagine these wandering worlds. The first lesson rogue planets teach us is that home is not always as fixed as it seems. Earth feels stable beneath us. The sun rises, the seasons return, the moon changes shape and then repeats itself. Our calendar is built on dependable motions. Even when our lives feel busy or uncertain, the sky keeps a kind of order. Morning follows night. Winter gives way to spring. The year closes and begins again. It is easy, living here, to think of planets as settled things, placed in their orbits like stones in a garden path. But planets are born in motion. They form in disks that shift, collide, migrate, and clear. Young systems can be crowded. Giant planets can tug smaller ones into danger. Passing stars can disturb distant orbits. Binary companions can slowly twist paths out of shape. A planet can belong for a while and then be released. Home, in planetary terms, can be temporary. That does not make Earth fragile in any immediate sense, so please do not let this become a new bedtime worry. Our solar system is stable on human timescales, and the sun is not about to misplace us behind the sofa. But rogue planets remind us that the order we see now is the outcome of a long history. Stability is something systems earn over time. The planets left in a mature system may be the survivors of earlier instability. Some worlds may have been lost before the final arrangement settled. Some may have collided. Some may have fallen inward. Some may have been thrown outward into the galaxy. The calm pattern we see can hide a restless youth. In that way, rogue planets are like footprints outside the family home, evidence that not everyone who began there stayed. The second lesson is that darkness is not the same as emptiness. Human senses naturally link light with presence. We see what shines or reflects. We notice lamps, stars, windows, planets bright in the evening sky. Darkness feels like absence, because our eyes find less to hold on to there. But astronomy has spent centuries teaching us that darkness often means hidden, not empty. Dark nebulae are full of dust and gas. Dark matter shapes galaxies, though it does not shine. Black holes reveal themselves through gravity and surrounding light. Rogue planets belong to this same broad lesson. A planet can be dark and still be real. It can be almost invisible and still have mass, gravity, weather, heat, perhaps moons, perhaps oceans. It can bend the light of a background star for a brief moment and then vanish again into ordinary darkness. The dark between stars may be filled with more worlds than we ever guessed, not glowing enough for our eyes, but still very much there. That idea changes the night sky. When you look up from Earth, you see a scattered pattern of stars. Perhaps you see Jupiter or Venus, bright and steady. Perhaps the moon is there, making the whole sky softer. But what you do not see may be just as important. Between the stars in the black spaces, there may be planets without suns. Some are giant, still warm enough to glow faintly in infrared if they're young. Some are old and cold, nearly impossible to detect. Some may be rocky and frozen. Some may be gas-rich, wrapped in deep atmospheres. Some may be moving with young stellar groups, not yet fully cooled. Some may be ancient wanderers that left their birth systems before Earth had complex life. They are not visible in the familiar sky, but they belong to the same galaxy. The empty-looking spaces are not blank. They are simply not speaking in light our eyes can hear. A third lesson is that planets are more than their surfaces. We often judge worlds by what we can picture from outside. Mars has red dust. Venus has clouds. Jupiter has bands and storms. Earth has oceans and continents. A rogue planet teaches us to think downward. The surface may be frozen, dark and quiet, but below it there may be heat. Beneath ice, there may be liquid water. Beneath water, there may be rock. Within rock, there may be radioactive decay, chemical reactions and slow circulation. A planet is a layered body, not just scenery. Its most important environments may be hidden from view. This matters especially for astrobiology. If life can exist in subsurface oceans or deep rock, then the best places to look may not always be the prettiest places to photograph. Some of the universe's most interesting habitats may have no sky at all. This is humbling because Earth's surface is so generous. We live under a transparent atmosphere, beside liquid oceans, beneath a stable star. Energy falls from the sky every day. Plants turn that energy into food. Weather moves water. The atmosphere shields us. The magnetic field helps protect us. The moon steadies Earth's tilt. The surface is not merely habitable, it is beautifully exposed. A rogue planet, if habitable at all, would likely be habitable in hiding. No open sunlight, no forests, no blue sky, no easy biosignature drifting in a friendly atmosphere for telescopes to read. If life exists there, it may be microbial, sealed under ice, powered by chemistry near vents. It would be life without sunrise, life without seasons. Life without the grand surface drama that makes Earth feel alive to our senses. And yet, if it were real, it would be no less profound. The fourth lesson is that the universe is better at making worlds than our old diagram suggested. Once, the word planet meant the few worlds orbiting the Sun. Then it expanded to include exoplanets orbiting other stars. Then it had to stretch around hot Jupiters, super-Earths, mini-Neptunes, circumbinary planets, pulsar planets, planets with extremely strange densities, and now worlds with no stars at all. Rogue planets ask the word planet to become more flexible. Some may form in disks and be ejected. Some may form directly from collapsing gas clouds and blur into the low-mass end of brown dwarfs. Some may be wide-orbit planets that look isolated because their stars are too far away to reveal themselves. Some may have disks, accretion, and tiny systems of their own. The category is messy, but the mess is honest. Nature is not built from our vocabulary. Our vocabulary is trying to catch up with nature. This does not mean definitions are useless. Scientists need definitions to compare data, build models, and communicate clearly. But rogue planets remind us that definitions are tools, not fences that nature must obey. Whether we call an object a free-floating planet, an isolated planetary mass object, a sub-brown dwarf, or a rogue world depends partly on mass, formation, context, and evidence. The object itself does not change when the name changes. It keeps moving. It keeps cooling. It keeps bending light if it passes in front of a star. The name helps us, but the world is older than the name. That is a useful thing to remember in science, and perhaps in other parts of life as well. Labels can guide us, but reality is allowed to be more complicated. The fifth lesson is about energy. We are used to energy arriving from outside. Sunlight, warmth, day. A rogue planet lives mostly on internal accounts: formation heat, radioactive decay, tidal flexing, gravitational contraction in giant planets, chemical reactions, insulation, stored warmth. It is a world powered by what remains inside, not by what shines above. This makes rogue planets feel quiet, but also persistent. Their energy sources are small compared with a star, but they can last a long time when protected by ice, rock, or thick atmosphere. They show us that habitability, geology, and weather can sometimes be driven by internal engines. A planet is not a passive stone waiting for a star to animate it. It is a physical system with its own depth. The sixth lesson is about scale. A rogue planet's path is not a neat orbit around a nearby sun. It follows the galaxy. Its year, if we can use that word loosely, is the long curve around the Milky Way. measured in hundreds of millions of Earth years. During one such sweep, stars are born and die, giant clouds collapse, spiral arms are crossed, civilizations could arise and vanish. The rogue planet continues through the broader gravitational field, carrying its cold surface and hidden interior with it. This scale makes human time feel very small, but not meaningless. It is the familiar science for sleep problem, isn't it? The universe is always much larger than the part of it we can comfortably fit in our heads. And yet here we are, thinking about it in a quiet room, turning impossible distances into a story gentle enough to fall asleep beside. Rogue planets also teach us that being alone is not the same as being disconnected. A starless world may not orbit a sun, but it still belongs to the Milky Way. Its atoms were made by older stars. Its motion is shaped by galactic gravity. Its path may have been altered by planets, stars, clusters, and clouds. If it has moons, it is the centre of a small local system. If it lenses a background star, it briefly touches our observations through light. Nothing in the universe is truly separate. The lonely planet is only lonely in one sense. It has no nearby star. In another sense, it is connected to everything by gravity, history, and matter. Even the darkest wanderer is part of the same cosmic fabric. This is why the phrase rogue planet can feel both dramatic and misleading. Rogue suggests rebellion, danger, a world gone bad, perhaps wearing sunglasses indoors. But most rogue planets are not doing anything mischievous. They are following gravity. Some were pushed away by the same physics that allowed other planets to settle into stable orbits. Some were born from clouds too small to become stars. Some are simply the natural leftovers of planet formation. They are not failures. They are outcomes. A planet around a star and a planet between stars are both products of the same universe trying many possible arrangements. The rogue world is not outside nature's plan. It is one of the plans. For us, though, they carry emotional weight because they remove the sun. The sun is so ordinary in our lives that we forget how extraordinary it is. It is there every day, even behind clouds. It warms the surface, drives the climate, powers food chains, sets our schedules, and marks time itself. We complain when it is too hot, miss it when it is absent, and rarely stop to think that Earth's entire surface story depends on a star at just the right distance, stable for billions of years. A rogue planet helps us see the sun again by imagining its absence. No dawn, no noon, no golden hour, no seasons driven by light, no photosynthesis across continents. The lack becomes a kind of mirror. By picturing a starless world, we understand more clearly what a star gives, and Earth in that mirror looks very lucky. Not magical, not chosen, not guaranteed, but fortunate in a precise physical way. We orbit a stable star. We kept an atmosphere and liquid water. We have internal heat and surface sunlight. We have a moon, a magnetic field, plate tectonics, chemistry, and time. Our planet is not the only possible kind of world, but it is the kind that allowed us to exist and ask these questions. Rogue planets expand the range of possible worlds, but they also deepen gratitude for this one. The warm room, the soft lamp, the ordinary morning, the ability to open a window and see daylight, these are not small things in a universe where many worlds may never know a sunrise. If life exists on rogue planets, it may be quiet beyond anything we normally imagine. It may be hidden beneath ice, perhaps around vents, perhaps as microbes living slowly in darkness. It may never build eyes because there is no light to see. It may never know a sky. It may never produce forests, songs, or creatures looking up in wonder. Or perhaps most rogue planets are lifeless, preserving only chemistry and cold. Either answer would be meaningful. If they are lifeless, they still show us how planets form, scatter, cool, and survive. If even one is alive beneath its ice, the lesson would be enormous. It would mean life can persist without a star, that the universe's habitable spaces are not limited to warm surfaces around suns, and that biology can hide in places where astronomy sees only darkness. We're not there yet. We have not found life on a rogue planet. We have not drilled into a hidden ocean between stars. We have not even counted the population with confidence. But science often begins in this exact position, with a few clues and a very large question. The first exoplanets were once uncertain. Black holes were once mathematical oddities. The idea of oceans under ice once sounded far more speculative than it does now. Over time, instruments improve, surveys expand, and the universe yields a little more of itself. Rogue planets are entering that stage now. They are moving from imagination into measurement, from isolated candidates into populations, from mystery into a field of study. And maybe that is the final comfort of this whole strange topic. The universe is not only the bright things. It is not only stars, galaxies, nebulae, and glowing explosions. It is also the quiet things, the hidden things, the cold things, the worlds that do not announce themselves unless gravity briefly bends a background star, the oceans that may never touch a sky, the moons that may circle dark giants, the planets that left home long ago and still continue, not as tragedies, but as travellers. Darkness in the universe is not empty space waiting for meaning. It is part of the meaning. So, dear listener, as we let this journey settle, picture one last rogue planet moving through the Milky Way. Perhaps it is a giant world, faintly warm inside, with storms rolling under dark clouds. Perhaps it is a frozen rocky planet with a hidden ocean sealed beneath ice. Perhaps it is small, cold and silent, with no atmosphere left at all. There is no sun in its sky, only distant stars. No morning waits over the horizon. No calendar turns by orbit around a local star. And yet the planet is not nowhere. It is in the galaxy. It is made of ancient star matter. It follows gravity. It carries a history. It may have lost a home, or it may have been born without one, but it still belongs to the universe. And here you are, on a very different kind of planet, held close to a star, wrapped in air, living under a sky that brightens every day. Maybe the room around you is dark now. Maybe the night outside your window is quiet. Maybe the stars are hidden by clouds or city lights. But somewhere beyond all that, the galaxy is full of motion. Stars are burning, new systems are forming, old worlds are cooling. And perhaps countless rogue planets are drifting through the spaces between, unseen but real, reminding us that home can be fragile, darkness can be full, and the universe is always larger and stranger than the small bright circle we know. If this quiet journey through starless worlds brought you a little calm, a little curiosity, or simply a softer place for your thoughts to rest, I would be ever so grateful if you liked the video, subscribed, and shared this sleepy corner of science with someone else who enjoys drifting through big questions at a gentle pace. And as you settle back into your own little orbit tonight, warmed by a star you may not see until morning, remember that even the loneliest worlds are not truly outside the story. They are moving with us through the same galaxy, under the same deep laws, through the same patient dark. Sleep well, fellow traveller, wherever you are, and whatever skies above you now.